Okay. Right. Yeah. So good afternoon to all. Good afternoon to everyone. Yeah. So welcome to the session, today's session. Yeah. So still the students are keep on joining. I'm just waiting. Okay. Yeah. Just a minute. Right. Fine. So in the last class, we have discussed about. Just a minute. I will switch on another light. Another light. Yeah. So in the last class, we were started about the alternator, the new topic, alternator operating on the bus bar. We are completed 2 alternates in parallel along with the problems, right? And you just to go through that questions that were given in the material booklet I have given at the end of the chapter in parallel operation of alternator objective questions, and all they are the some of the competitive examinations only. I have given all the questions are from competitive examinations only. You just go through that. Now you are in a position to answer all type of questions. Okay. And coming to the alternator operating on the bus bar, alternator operating on the infinite bus bar. So when terminal voltage, alternator connect to the bus bar means its voltage and frequency constant. The main difference between single alternator, 2 alternates in parallel, alternator and bus bar is, if excitation changes, in single alternator voltage increases, excitation increases, voltage increases. Even 2 alternates also, if excitation of any one machine increases, the set terminal voltage will increase, or vice versa, decreases. But an alternator operating on the infinite bus bar, its terminal voltage remains constant. Whether you increase excitation or decrease excitation, voltage is not going to be changed. Why? Because infinite number of alternates are already there. So single alternator, if you change, nothing is going to happen, no change. And its speed also will be remains the same. An alternator operating on the bus bar, if you change the speed, a prime mover input, there will be no change in its speed. There is no change in frequency. So yesterday I was explained, na? Yes. Why? Because when prime mover input increases, it delivers the power automatically. When mechanical power input increases, it delivers the power, right? And that will be going to the loads. So it will automatically take the load. It will automatically take the load. So when prime mover torque increases, electromagnetic torque increases automatically, because infinite loads are there. But a single alternator, loads are fixed. Loads are fixed, right? But an infinite alternator, infinite number of loads means how much power you give, that much power it will take, right? So load falls automatically, it will maintain the speed constant, right? Yeah. And coming to its terminal voltage also will maintain constant always. Terminal voltage also will be maintained constant. Why? Because the reactive power will comes into picture. The reactive power will comes into picture. If you are increasing excitation, say, it will demagnetize. Over excitation condition, it will be demagnetized. Under excited condition, it will be magnetized. When you are giving less field current, so reactive power will comes into picture. It is aiding magnetizing, so that net flux is maintained constant always. When flux constant means terminal voltage is also automatically maintained constant. Right? Yes. But alternator, as I have given, based on the excitation, 3 modes of operation. Dear student, 3 modes of operation. What is that? Number 1, over excitation, under excitation, normal excitation. That is, if E cos delta, Q is equal to V by XCS, E cos delta minus V, na? Yes. So if E cos delta greater than V or less than V or equal to V, that is the deciding factor. Over excitation, the machine will deliver E cos delta greater than V. Under excitation, the machine will absorb the reactive power. Normal excitation neither deliver nor absorb the reactive power. Right? The synchronous machine, it can deliver or it may absorb, depends on your excitation, or it may not be absorbed, delivered also, because you give sufficient field current. If you produce required air gap flux, no need of any AC reactive power. Compulsory flux is needed. Flux you are providing, machine cannot absorb. But whereas induction motor is there, na? For induction motor, you are not, it is singly excited. You are not giving any excitation from the rotor side. So definitely, it has to produce its reactive power totally from the armature side or stator side. So induction motor, induction generator, always they absorb the reactive power to magnetize the core for the production of working flux. Right? Yeah. Now, in this class, we are going to continue the same thing. In alternator, two alternates in parallel, we have seen the two topics. Yes, we have seen that two cases: effect of change in excitation, effect of change in mechanical power input. Here also same topic. So alternator means controlling is possible only from input side. Therefore, we are going to see change in excitation, effect of change in excitation, effect of change in mechanical power input. First, we will see under no load condition. After that, we will come to the load condition. So the next heading is, this is effect of change in excitation. Effect of change in excitation under no load condition. Effect of change in excitation. Effect of change in excitation. First, no load condition. We are going to see no load condition. First, under no load condition, right? The alternator operating on the bus bar. See, this is alternator connected to the bus bar. Of course, all conditions are already verified. All the conditions are already verified and it is connected, say, connected to the bus bar. Yeah. This side, of course, I am not drawing every time. This is left side, infinite alternates are there, no? Infinite alternates are there. Right side, infinite loads are there. That I am not drawing. This is itself infinite bus bar. This is the bus bar. Okay. I hope you understood. This is left side, infinite number of alternates are there. Right side, loads are there. Okay. Yeah. And first, if you want to operate this machine, this left side and right side, I'm not drawing. It is understood that what will be there? Loads are there. First of all, if you want to operate this machine under no load condition, what to do? Tell me. If you want to operate under no load condition, the mechanical power input is given only to meet the losses. Mechanical power is given only to meet the losses. Okay? That is P mechanical is equal to P mechanical is equal to meet the losses. Correct? Mechanical power input is equal to P mechanical is equal to only to meet the losses. So whatever the power input is given, only to meet the losses. When power input is losses means what is power output? Power output is equal to 0. Power output is 0. It is generating the voltage. It is generating because we have given field current. It is generating the voltage. In the armature winding, it is generating the voltage. and the generated voltage say E. Generated voltage is E. Terminal voltage, it is V. Of course, terminal voltage is remains constant. Terminal voltage is always constant, na? Yes, V is always constant. V always constant. And when excitation changes, E will change. When excitation changes, V will change. Right? Yeah. But power is equal to 0. Power is equal to 0. You mean to say under no load condition. See, under no load condition, mechanical power input is given. P mechanical power input is equal to how much? Only to meet the losses. To meet the frictional losses and while rotating, to meet the losses. Therefore, power output is 0. Power output is 0. When power output 0 means, what is power? Power is equal to EV by XS sin delta. EV by XS sin delta 0. That is equal to delta is equal to 0. Delta is equal to 0. Fine? Yeah. And we know E is equal to what? V plus J into IAXS. This will be always. And Q is equal to V by XES. Q is equal to V by XES. E cos delta minus V. This is of course general relation. These are the general relations. Correct? E is equal to V plus IAXS. And Q is equal to V by XES. E cos delta minus V. But delta is equal to 0. Delta is equal to 0. Fine? Yeah. Now under this, there are various conditions we are going to see. Based on the excitation, of course it is no load condition. No load condition means we are not separately connecting a load on that. You give mechanical power input. As I told now, so power can be controlled. Load can be controlled only from prime mover side. Load cannot be controlled from load side. Loads are somewhere. Whatever you want to controlling is possible only from input side. Reactive power can be controlled with excitation. Active power can be controlled from prime mover side. Because infinite alternates are there and all that transmitting the power, loads are somewhere, infinite loads are there. One particular load is not related to one particular alternator. So load control is only from input side. That's the reason if you give power input only to meet the losses, right? The prime mover torque is equal to B into omega, frictional losses. Just for rotation purpose, whatever your power is giving, it is generating the voltage, it is rotating at synchronous speed. Right? Yeah, it is rotating at synchronous speed only. It is rotating at synchronous speed. But power output is equal to 0, delta 0. Okay. So under this, there are three modes of operation. One is normal excitation, under excitation, over excitation. So let us discuss those things. First one, normal excitation. Let me start. Number one, normal excitation. For normal excitation, E cos delta. Normal excitation, E cos delta is equal to V. But what is that E? E is equal to V since delta is equal to 0. E cos delta is equal to V means E is equal to V. The normal excitation means E cos delta is equal to V. If you draw this, this is E phasor and this is V phasor. Both are in same phase. V and E both are in same phase. This is E, that is equal to V. When both are in same phase means what is the potential difference? Potential difference is 0. When potential difference is 0 means what is the current? Current is 0. See here from this IA is equal to E delta minus and E minus V by XES. RA neglected say. RA neglected. E minus V by XES say or ZS. What is that? That is equal to 0. Current is 0. Or XES. Let me take RA neglected XES. Current is equal to 0. When current is 0 means what is the power? Tell me. Active power is equal to V into IA cos phi. That is equal to 0. And similarly reactive power Q. Q is equal to V into IA sin phi. That also equal to 0. The machine is connected to the bus bar. Okay, machine is connected to the bus bar, but it is not delivering any power, not taking any power. No active power flow, no reactive power flow. Machine is just connected. It is rotating. Machine is rotated, driven the prime mover, but no load condition, small amount of power input is enough. Okay, yes. So it is rotating, but it is not taking any power because power input is given only to meet the losses. So no active power flow, even no reactive power flow is there. No reactive power flow. This is said to be, this condition is said to be, machine is said to be floating on the bus bar. Machine is said to be floating on the bus bar. There is no active power flow. There is no active power flow, active and reactive power flows. Reactive power flow. Machine is just connected. The machine is just connected to the bus bar. Just connected to the bus bar. Bus bar. This is said to be, machine is floating on the bus bar. Therefore, the machine is said to be, the machine is said to be floating on the bus bar. Floating. This is called what? Floating on the bus bar. Floating on the bus bar. Right? What is Pujita? Hello, some of you are raising your hand. Is there any problem? Voice problem? Pujita. Hello? Hello, Pujita. You have raised, some people are raising. Okay. Right. Yeah. This condition is said to be called what? Floating on the bus bar. This is said to be floating. Alternator is said to be floating on the bus bar. The floating means simply machine is connected, no power flow. It is not doing any work. It is not doing any work. Okay. Yeah. So I hope you understood now. This is a alternator. This side infinite loads are there. I am not showing left side, right side. Yesterday I have shown infinite number of alternators are there left side. Infinite loads are there. But you are giving power input only to meet the losses. So therefore it is not taking any power. It is not taking any power. And beyond that power input, still you increase the power input, then delta will comes into picture. Then rotor pulse leads. Then phase are different. Then it will power flow takes place. But we were discussing the yes, no load condition. Next, this is for normal excitation. Now second one, under excitation, say under excitation, over excitation. Second case, over excitation. Second one is over excitation. For over excitation means that is E cos delta greater than V. E cos delta greater than V means E greater than V. E greater than V. Draw the phasor. See, this is E. This is E. And this is V. Delta 0. Therefore, both will be in same phase. E and V both are in same phase because no load condition delta 0. E, V both in same phase. But this is EV means we know E is equal to V plus J into IAXS. Na? E is equal to V plus J into IAXS. Therefore, the drop must be added from the tip of V vector. So IAXS will be in this direction of V to E always. That is IA into XES. IAXS is upwards direction. V to E. It is V to E. IAXS upwards direction. And this is IAXS. Now IA will be in this direction. This is IA. IA is here. This is IA. IA. So IA lags this V by 90 degrees. Current IA lags V by 90 degrees. When lag means machine is operating at ZPF lagging. Machine is said to be operating at 0 power factor lagging. Okay. Yeah. Now IA power flow takes place. IA there, but it is IA lags. IA lags. IA lags the V by 90 degrees. Therefore, the machine operate at ZPF lagging. Machine will operate at ZPF lagging. ZPF lagging. Then what is armature reaction? Armature reaction is purely demagnetization. Armature reaction is purely demagnetization. It's a purely demagnetization. Demagnetization, and will be there any active power flow takes place? No active power flow, because see, P is equal to V into IA cos 90. V into IA cos phi. Phi is equal to 90 degrees. Phi is nothing but angle between V and E. Sorry, V and IA, power factor angle. So that is equal to 0, Q0, P0. And what about Q? Q is equal to V into IA sin 90. V into IA sin 90 means it is V into IA. V into IA. Okay, yes. And E cos delta greater than V. If you take E cos delta greater than V, E cos delta greater than V, therefore Q is positive or negative? Q will be is positive. Q positive means therefore Q will be deliver. The machine will deliver the reactive power. Machine deliver the reactive power. Okay, the machine is connected here. It is connected on the bus bar, but it will deliver. The machine deliver the reactive power. Deliver the active power is 0 only. P is 0 only, but it will deliver the reactive power. This is V, say, this is V constant, but E is increasing. Na? We have increased excitation. When excitation changes, E has increased. E changing, E is not constant, E is variable. When E greater than V, therefore the machine will deliver the reactive power. Q will be delivered. Q delivered. Why? Because this is which component of the current? That is IA sin phi component. It is IA sin phi component. IA is there. IA is delivering, na? Yes. This IA is it IA cos phi or IA sin phi? IA sin phi. Machine will deliver the reactive power. Since E greater than V. Because E greater than V, na? Yes. Deliver the reactive power. And one important thing, dear students, see, some students may be getting a doubt. How I am drawing this phasor? First, I am drawing E and V. But E magnitude greater than V, na? E is greater than V. Delta 0. That's the reason both are in same phase. Delta 0 means both are in same phase. Now, if you draw V and E, based on this relation, E is equal to V plus J into IAXS. Based on this relation, always drop will be added from the tip of V to E. E is equal to what? V plus J into IAXS. V plus J into IAXS. And then IA will be, if IAXS upwards means IA will be lagging, na? Yes, IA. Whenever you are getting a doubt, you please make a note this point. What is that? IA lags the drop. IAXS drop lags IA by 90 degrees. By 90 degrees. It is fixed everywhere. Or IA. No, IAXS drop leads the IA. Not lags, leads the IA. Leads IA by 90 degrees. Or IA lags the IAXS drop. IAXS drop by 90 degrees. Correct? Yes, everywhere. That is not necessary to be alternator, even network T everywhere. Reactance drop leads the current, na? Yes, reactance drop leads the current. Our current lacks the drop. Whether it may be inductive or capacitive, whatever it may be. From here onwards, first what I will do, I will draw the drop, I will draw. Then I will draw the current. First draw and then current. Okay. Generally, we will draw first current and drop, na? Yes. Because I don't know current which direction. E I know, V I know. Simply join V to E. Drop you will get. Now current will lack the drop. Okay. Yeah, fine. And main important thing is here the machine is operating at what power factor? ZPF lagging. ZPF lagging. Okay. Now, next this is over excitation. Let us take for under excitation. Next, under excitation, if you take for under excitation. Third case, under excitation. Under excitation means that is E cos delta less than V. E cos delta less than V, therefore E less than V. E less than V. Draw that. This is V and this is E. This is E. Then what is the direction of drop? Drop is downwards. No? Drop is V to E. This is J into IAXS. That is a drop. When that is downwards means IA will be in this direction. This would be the IA. This is IA. So, IA. Now phasors are rotating. Then what is happening? IA? IA leads the V by 90 degrees. IA leads. Power factor is angle between V and IA. Okay? Power factor is angle between V and IA. IA leads the V by 90 degrees. See. IA leads the V by 90 degrees. 90 degrees. Therefore, machine operated ZPF leading. Machine operated ZPF leading. And the armature reaction, effect of armature reaction. Effect of armature reaction is purely magnetization. Effect of armature reaction is purely magnetization. And if you calculate active power P, P is equal to V into IA cos 90, that is equal to 0. P 0 and Q is equal to V into IA sin 90. That is equal to V into IA. V to IA. And since E cos delta less than V. E cos delta less than V means Q is negative. Q is negative. Okay, yes. Q negative means therefore Q will be absorbed. The machine will absorb the reactive power. Q negative means Q it will be absorb the reactive power. Absorb the reactive power. When machine connected on the grid, it will absorb the reactive power. Right? Of course, active power P is equal to 0, but it is absorbing the reactive power. Absorbing the reactive power. Q absorb. Only reactive power flow is there. Q absorb. Active power is 0. And from this, the main observation, dear students, the main observation is power factor is ZPF leading. The machine operated ZPF leading power factor. And earlier, power factor is ZPF lagging. ZPF lagging. In no load condition, what is the power factor? Power factor under no load condition is ZPF, 0 power factor. It may be lagging or leading. Power factor under no load condition is 0 only. Why? Because active power is 0, na? Active power is 0. Power factor under no load condition. under no load condition is nearly zero. Is nearly zero. It may be zero lagging or leading, nearly zero. Because the power is zero, active power is zero. If losses are neglected, active power is zero. When power is zero means power factor is zero, na? Yes. Since power is zero, power factor is equal to zero. This is not only for synchronous machine, everywhere, in all the machines. I think you might have completed already induction motors or transformer. Transformer also, what is the no load power factor? Very less, 0.1 lagging, 0.2 lagging. If losses are neglected, that is also zero. For induction motor also, no load condition, 0.1, 0.2 lagging. 0.1, 0.1 at almost zero. Losses will be there, that's the reason they will take some active power. Some active power they will take, no load condition also, because to meet the losses. That's the reason you may expect 0.1 lagging. Otherwise, losses are neglected, ideal cases, power factor is zero under no load condition. Because power is zero, active power is zero. Power factor is proportional to VI cos phi. Yes. Like here also it will be same. Okay. Yeah. And these things we are going to see. And same even motor under excitation, power factors are quite opposite. Power factors are quite opposite. Okay. Fine. This is under no load condition. Therefore, we observed that under no load condition, the machine will be only either delivering or absorbing the reactive power. No active power flow. No active power flow. So under no load condition, under no load condition, under load condition, it is observed that there is no active power flow. There is no active power flow. There is no active power flow. Only reactive power flow takes place. Only reactive power flow takes place. So don't think current is not zero. No load condition, current is there. Which current is there? Tell me. IA sin phi component. This is there. Which component is IA sin phi is there? IA is not zero. IA sin phi is observing. IA cos phi. Magnetizing current it is only. Magnetizing current. Right? It is causing demagnetization, magnetization. Active component is zero. No load condition, active component is said to be zero. Okay, yes. Fine. But load condition, we are going to see again. Load condition, it is not like that. Load condition, active component also will come into picture. Yeah. One question for you in one of the examination. One of the examination is given like this. See, the question is, an alternator is floating on the bus bar. An alternator is floating on the bus bar. An alternator is floating on the bus bar. If the excitation is increased, the excitation is increased, then its power factor would be, a bit. 0.8 lagging, B bit. ZPF lagging, C bit. 0.8 lagging, 0.5 lagging, C bit. ZPF lagging and D bit. ZPF leading. Okay. What is your answer? An alternator is floating on the bus bar. If the excitation is increased, then its power factor would be. What is power factor? Right? Its power factor would be. Its power factor will be ZPF lagging. When excitation is increased, it means it is already floating condition. Floating means what is the floating condition? Floating means normal excitation, E is equal to V. And then when excitation is increased, it means it is over excitation. First of all, you should know floating. Floating means no load condition, normal excitation. Normal excitation. Right? When excitation increases, it becomes over excitation. Then its power factor will be lagging, ZPF lagging. Okay. You should understand, first of all, floating means, I have given now already, floating. What is the meaning of floating? Floating takes place under no load condition, for normal excitation. For normal excitation. I have given already this, normal excitation. Okay, yes. And when excitation is increased more than that, over excitation. Fine. This is about no load condition. Now let us discuss under load condition. Load condition is power factor is not zero. Load condition, power factor is not zero, because power will comes into picture. So let us see now load condition, effect of change in excitation under load condition. Effect of change in excitation load conditions. Load condition, effect of change in excitation and mechanical power input is kept constant. We are changing excitation. What about mechanical power? Other input will be kept constant, is understood. One input changing means other is understood constant. Mechanical power input or prime mover input is kept constant. Mechanical power input is kept constant. So alternator operating at the bus bar is connected to the bus bar but load condition means what to do? Prime mover input has to be given. The prime mover input has to be given to the rated value. But that prime mover input is kept constant. This is the prime mover. The armature winding, this armature winding. EMF will be induced in the armature winding. So for the prime mover, we are giving rated mechanical power input. Or P mechanical is kept constant. In other words, what? P mechanical is kept constant. Mechanical power input is kept constant. When mechanical power input is constant, electrical power output also constant. Right? Mechanical power input is constant. Electrical power P is constant. Electrical power output is constant. That is P. P electrical is constant. And mechanical power constant means electrical is constant. Of course, terminal voltage is always constant. This is V. Terminal voltage will be always constant. And what about excitation? Excitation changes. Why? Because we are changing field current. If you are changing field current, say, when we are changing field current field current changes, E changes, excitation changes. When excitation changes, reactive power also will changes, na? Yes. When excitation changes, reactive power flow also changes. Q and Q. It may be delivered or it may be absorbed, but that Q also will change. Why? Because E changing, Q will change. P constant. When excitation changes, E changes. E cos delta also changes, na? Yes. So that's the reason the reactive power will changes. And we are rotating, this machine is rotating. Prime mover torque is given. It is rotating at synchronous speed. And when electromagnetic torque is there, means power is there. Electromagnetic torque also will in which direction? Opposite direction. Electromagnetic torque will be in opposite direction. Machine is working. Machine is running at synchronous speed. Electromagnetic torque in opposite direction. Machine is working under steady state condition. Say it is operating at rated condition. Rated mechanical power input is given. Rated electrical power it is delivering. And where that power will go? They will go to the loads. Loads are connected right side. I am not showing. Okay. Infinite alternator this side and infinite loads right side. It is understood. Okay. So in this mainly power is equal to EV by XS. EV by XS sin delta, and that is also equal to V into IA cos phi. That is constant. Active power constant. Why? Because P mechanical is constant. Mechanical power is constant. Therefore, active power is constant. EV by XS sin delta constant. But here V and XS always constant. Na? V and XS always constant. Very important topic we are going to see. Dear students, same topic will be repeated for synchronous motor. But I will explain very clearly here. Synchronous motor, no explanation is required. Just quite opposite of that. Okay, I am going to write the conclusions there straight away. So therefore, you focus on this. V and XS. Vxs constant, na? Yes. Vxs constant. Then power is proportional to what? Power is proportional to only E sin delta. From this above equation, no? This is power is equal to EV by XS sin delta. But V and XS both are constant. When these are constant, it means power is proportional to only E sin delta. E sin delta. Then E sin delta also must be constant. E sin delta also must be constant. Then only this total power is constant, correct? Then only this total power is constant. Similarly, power also proportional to IA cos phi. VI cos phi, na? IA cos phi. Therefore, IA cos phi also must be constant. IA cos phi must be constant. Right? And E is equal to, this relation always valid. E is equal to V plus J into IAXS. And Q, I am neglecting RA throughout our expression. Throughout our discussion, I am neglecting RA. Q is equal to V by XES, E cos delta minus V. Okay? Yes. So this is E and this is Q. And here important thing is E sin delta is constant. E sin delta is constant and IAXS is constant. This is the main important thing. Okay, this is the main important thing. Why they are constant? Because these are constant, na? Because these are constant. Why? Because these are constant. From this equation, total power constant. VI cos phi, they will be constant. Okay. So these are the main important conclusions we are going to observe from this. From these conclusions only, I am going to draw the phasor diagram of alternator. So I hope the diagram is clear for you now. Yes, mechanical power is adjusted, rated, it is kept constant. Now I am changing the excitation. Now we are changing the excitation. Based on that, E changes, then reactive power flow will be changes. Over excitation deliver, under excitation will be absorb. Yeah. Based on this, let us draw the phasor diagram of alternator. Next page I am going. But remember, E sin delta constant, Ia cos phi constant. That is medium. See, this is V. Terminal voltage V. V I would like to take as a reference. V as a reference. Now drop will be okay. Yeah. Space I am just adjusting. Yeah. This is V, and a drop will be this side. This is yes. That is J into IAXS. J into IAXS. Sorry, because this diagram is important. That's the reason I want to get the whatever. B. Now this is IAXS drop. V. J into IAXS. Now what is this? This will be the E. If you join these two, this is E. This is E. Okay. This is J into IAXS. J into IAXS. So V plus J into IAXS. Then this is J into IAXS means what is IA? IA will be perpendicular to this. Na? Yes, this IA will be perpendicular to this. This is IA. This is IA. Because IA is always perpendicular to the drop. IA will be always perpendicular to the drop. Is it clear? See, this is V. I am adding IAXS drop. Then this is the E. This is the E. Now, IAXS is like this. IA is perpendicular. IA and IAXS perpendicular, na? Yes. So this is IA. IAXS is this side. That will be perpendicular. Okay. This is delta. No, this is delta. What is this? This is phi. Power factor angle phi. Power factor is angle between V and IA. V and IA. Terminal voltage and current. Terminal voltage and current. Machine is delivering the current, na? Yes. So that is V and IA. Lagging power factor. Lagging power factor. Now, let us divide that E into two components. E into two components. E can be divided into two components. This is one component. This is another component. E can be divided. This is E sin delta. Okay. But E sin delta will be constant. Na? E sin delta will be constant. E sin delta constant. This is E cos delta. This is E cos delta. E cos delta. E cos delta. Correct? One component is divided along V, another component is divided along the perpendicular component. So therefore, this component is E cos delta, this is E sin delta. E cos delta, E sin delta. Since E sin delta constant means, if E sin delta constant, then this will be the locus of E. This will be the locus of E. This is locus of E. Because this width must be constant, no? Yes. This is E. So locus of E. Locus of E. The tip of E vector will be on this line. Locus of E. Why? Because E sin delta constant. E sin delta constant. So therefore, this E sin delta must be always constant. So E cos delta is E sin delta component. It will be parallel to the V. Parallel to the V. This width must be constant. E sin delta should be constant. Okay. So it is locus of E. Similarly, Ia cos phi. This is Ia cos phi. Okay, this is Ia cos phi. But Ia cos phi also must be constant, na? Do you remember earlier we have taken, based on this I am writing, dear students, E sin delta must be constant. Ia cos phi must be constant. Ia cos phi must be constant. E sin delta constant. So this is E sin delta. Its width must be constant. Its width must be always constant. So this is the locus of E. Locus of Ia means E phasor must be always along this line. Always along this line. Similarly, Ia cos phi. This is locus of Ia. Ia cos phi will be always along this line. Ia cos phi will be always along this line. Because here Ia cos phi must be constant. This is Ia cos phi. This is Ia cos phi. That also must be constant. That also must be constant. Therefore, tip of Ia phasor will be always along this line. Tip of Ia will be always along this line means this will be the locus of Ia. This is locus of Ia. Locus of armature current Ia. Locus of Ia. Right? Yeah. Listen, once again I am explaining. See, dear students, listen. This is V. This is terminal voltage V. I am adding Ia excess drop. Okay. Now this is E, joining V to E. E angle between V delta, and this is phi. This is phi. Okay. Ia should be how? Ia should be perpendicular to Ia axis. First I am drawing Ia axis. I am just extending this dashed line, showing that Ia must be perpendicular to that. This is Ia. But E sin delta, E can be divided E cos delta, E sin delta. But E sin delta should be constant, means this should be the locus of E, locus of E. And similarly, this is Ia. And vertical height, Ia cos phi. This is Ia cos phi. So therefore, the locus of Ia will be this. Then only this Ia cos phi also must be constant. This constant. Ia cos phi must be constant. Okay. Now, this is for one particular excitation. See, for example, this is E1 excitation, E1 say. This is E value that is equal to E1. E1. Now, decrease excitation. We are changing excitation. Na? Effect of change in excitation means in this alternator, we are changing excitation. We are changing excitation. When excitation changes, E changes. Magnitude of E will be changes. E changes. So when E changes, see. E changes, E decreasing. I am reducing that E. See here, this is Ia axis. This is E. E2 say. What is this? This is E2. E2. Yeah. E2. Excitation is reduced. E2. But when this is E2, what is the drop Ia axis? Ia axis must be join V to E. Join V to E means this is J into Ia axis drop. What is this? This is J into Ia axis drop. Ia to axis drop. This is J into Ia1 axis drop. Ia1 axis. Now, similarly, E3. But this is Ia to XCS. Important thing is I am joining simply V to E, Ia XCS. Once you know the drop, how the current will be? Current current is perpendicular to this drop. Current will be perpendicular to drop. Okay, IA2 must be like this. This would be IA2. IA2. Why? Because that is perpendicular to IA axis. IA axis is like this. So IA must be perpendicular. IA must be perpendicular. Just like here also same thing, na? IA1 axis is like this. This is IA1. This is IA1. Okay, IA1. That IA1 is perpendicular to IA1 axis drop. Similarly, but this E2 is said to be normal excitation. Na? So earlier this is delta 1 say. So for example, earlier this is delta 1. Na? This is delta 1. What is this? This is delta 2. Delta 2. When delta 2, what is E2 cos delta 2? E2 cos delta 2. This is E2 cos delta 2 is equal to V. E2 can be divided. E2 cos delta 2 is equal to V. That is said to be normal excitation. Na? Yes, E2 is said to be normal excitation because E2 cos delta 2 is equal to V. Normal excitation. For normal excitation, what is power factor? UPF. IA2. IA2 in phase with V. In phase with V. That is the power factor is said to be UPF. The current is delivering. Machine is delivering the current. Na? Yes, machine is delivering the current and the bus bar, that is a V. When it is delivering the current, power factor is nothing but angle between V and IA. V and IA. So therefore, IA is in phase with V, power factor is UPF. UPF. Okay? Yes. Machine is operating at UPF. And some students will raise a doubt. Sir, are we connecting a resistive load there? No, loads are somewhere. Dear students, loads are somewhere. I don't know, whatever the all varieties of load are there. But I can operate my machine at any power factor. I can operate my machine at any power factor based on the excitation. So for normal excitation, it is operating at UPF. UPF. Okay? Yeah. Now, then still decrease the excitation. Let us decrease the excitation. E3. I am reducing excitation. See, this is E3. E3. Still reduce excitation. E4 say. Under excitation. We are coming to the under excitation. Under excitation. This is E3 and this is E4. 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 Okay. Now join IA1 XCS, IA3 XCS. So these are the drops. Na? This is IA1 XCS drop. I am changing the color. This is, just let me change the color. Okay. I'm changing the color for clarity. This is IA1 drop color. Say, I'm changing drop color. This is IA1 XCS. This is IA2 XCS. And what is IA3 XCS? This would be the IA3 XCS. This is IA3 XCS. And this is IA4 XCS. IA4 XCS. J into IA3 XCS. J into IA3 XCS. What is this? This is J into IA4 XCS. J into IA4 XCS. Okay. Now another important observation. See, another important observation for normal excitation. You please observe normal excitation. E2 is there na E2. That E2 means E2 cos delta 2 is equal to V. But what is this? This is E2 sin delta 2. E2 sin delta 2, of course, that is equal to IA2 XCS. IA2 XCS. But E1, that is equal to, initially this is E1 sin delta 1. Can I say it is also equal to E2 sin delta 2? This component, that is equal to the same or not? Yes. Both are same. This E2 sin delta 2 is equal to E1 sin delta 1. From this we observed that E1 sin delta 1 is equal to E2 sin delta 2. E2 sin delta 2. And not only that, that is also equal to E3 sin delta 3. You can observe from the diagram. You can observe. When it is observed, when it will be possible. So locus of E will be along this line. That's the reason I am writing E2, E3. That will be on this line. Tip of E will be here. Okay. Even E3 sin delta 3 also you will get the same thing. Yeah. Now, this is E3, E4. Based on that, draw the current. Draw the current. IA3 axis is there, na? IA3 will be perpendicular to that. This is IA3. This is IA3. So that IA3 will be perpendicular to that. IA3. Now IA4 will be perpendicular to this. IA4 will be perpendicular to this. This is IA4. IA4. Okay. Only tip of IA will be along this locus of IA. Are you getting? IA vector will be always along this line. Along this line. Then only you can find IA cos phi will be same. IA cos phi 1. You can also observe here IA1 cos phi 1. IA1 cos phi 1 is equal to IA2 cos phi 2. That is also equal to IA3 cos phi 3. That is required, na? Yes. That's the reason IA, locus of IA, locus of E. Locus of E. Okay. So from this, yeah, IA. Now this is phi 1. What is phi 1? Delta 1, delta 2. Let me change the color of delta 1. This is delta 1. Na? This is delta 1. What is this? Delta 2. This is delta 1. Black color I am in. Delta 1, delta 2. What is this? This is delta 3. Na? Yes. This is delta 3. Delta 3. And similarly, delta 4. This is the delta 4. Delta 4. Okay. Yes. As delta increasing. Delta increasing. What about phi power factor? Power factor angle is equal to, this is phi 1. I am using green color, phi 1. What is phi 2? Phi 2 0. Phi 2 0. But this is phi 3. Phi 3. And phi 4? Phi 4 is nothing but, this is the phi 4. This is a phi 4. Phi 4. Power factor angle. So power factor angle between V and IA. V and IA. Delta is the angle between E and IA. Okay. Observation is now coming to the conclusions. See, I have kept load constant only. Dear students, power input constant means active power constant. When active power constant means alternator is supplying constant power only, and it is taking constant load. Then primary input constant means load also said to be constant. Load also constant. Right? Yes. But when load is constant, even active power is constant, that is load is constant, but current is not constant. IA1 changing, IA2 changing, IA3, IA4, current is changing. Right? But power constant, but why current is changing? When power is constant, why current is changing? Why current changing? Because power factor is changing. I cos phi must be constant. This IA cos phi must be constant. Okay, but when power factor changes, current also changes. Power factor changing, current changing. Why power factor changing? We are changing excitation. So therefore, power factor changing, current is also changing. Current changing. Now, and another question for you is, why delta changing? Load is constant. Load is kept constant. Load constant means primary input constant or output constant. It is taking the same load. Load constant. But why load constant? Delta, why it is changing? Power constant. But why delta changing? Because power is proportional to E sin delta. Okay. Power is proportional to E sin delta. Not just delta. Power is constant, but when E changes, delta should be what happened? Delta. Delta should change. Okay. When E is increasing, say delta is reducing. Are you observing same thing or not? If excitation increases, what will happen? Sin delta has to reduce. That is what you can observe here. As E increasing, say, for example, E4, E3, E2, E1. Deltas are changing. When excitation is more, delta 1 is less. See, excitation is more. This is delta 1 is less. When excitation is decreases, delta increasing. Delta increasing. And power also proportional to cos phi. IA cos phi. IA cos phi. IA is not constant. Why? Because power factor is changing. Power factor is changing. But P constant. P is constant. Okay. Let us see. In this, E1 is said to be over-excitation. Dear student, E1 is said to be over-excitation. For over-excitation, what is the power factor? Lagging. IA1 lag. IA1 lag. And E2 is said to be normal excitation. because E2 cos delta 2 is equal to V, normal excitation, machine operated UPF. Similarly, E3 is said to be under excitation because E3 cos delta 3 less than V. E3 cos delta 3 less than V. It is operating at under excitation. For under excitation, what is the power factor? IA3 leading. And similarly, E4 cos delta 4 also less than V. That is also said to be under excitation. What is its power factor? Leading. Its power factor also leading. Correct? Yes. From the diagram, we can observe that E1 cos delta 1 is greater than V. That's the reason what is the power factor? Over excitation. That power factor is said to be lagging power factor, lagging. But E2 cos delta 2, that is equal to V, normal excitation. Normal excitation, what is the power factor? UPF, you can observe, UPF. Similarly, E3 cos delta 3. E3 cos delta 3 is equal to, is less than V. Then it is said to be under excitation. For under excitation, what is the power factor? Leading power factor. This is what we observed, leading power factor. Okay. Similarly, E4 cos delta 4 also less than V. That is also leading power factors. And the current is varying, power factor is varying. No? Yes. The current is varying and power factor is varying. Variation of current is a V curve. Power factor variation is inverted V curve. See the variation. I am drawing variation. The current variation, how it is with respect to excitation. See, from the graph you observe. The next page I am going to draw very clearly. See, current and power factor. First, let me draw the current. Current here, minimum excitation. From minimum excitation, let me go. This is IF. Now, IF is nothing but excitation. Among all, which is minimum excitation? E4 is the minimum excitation. Minimum excitation is E4. E4 is minimum excitation. But current is maximum. Now, IA4 is maximum. With minimum excitation, current IA4 is maximum. Therefore, let me draw. This is for this excitation, current is maximum. Okay. For this excitation, minimum excitation, E4, current is maximum. Now increase the excitation. When excitation is increased to E3, IA3 reduced. When compared with IA4, IA3 reduced. Correct? E3, excitation increased, IA3 reduced. When I am increasing excitation, the current has reduced. Similarly, increase excitation to E2. Okay? E2. First E4, excitation increases E3, next E2. When excitation increases to E2, current has still reduced. IA2 reduced. Na? Yes. IA4, IA3 decreasing, IA2 still decreasing. Therefore, when excitation E2 means IA2 still reduced. IA2 is reduced. When excitation is increases, IA still reduced. Okay, yeah. Now, and beyond that E2, we are at E2, na? Normal excitation. Current is minimum. For normal excitation E2, current is minimum. Now increase excitation E1. When excitation increases, now current is increasing in this direction. Now it is lagging side, it is increasing. Lagging side. Fine? Yes. When excitation is increases, this is increasing again. This is increasing. Still you increase means the IA4 is going to be like this. If you increase that, then you can expect this may be the IA. This may be the IA. So IA, still more than that, if you increase, you can observe it is going to be still increases. Of course, I am not showing that one. It is understood that. So therefore, what is this? This is said to be current variation. So current is a V curve. Variation of current is a V curve. Is V curve. IA variation. This is IA. IA variation is a V curve. Correct? Very simple. You see, IA4 decreasing, IA3. IA4 ante under excitation, IA4 decreasing, IA3 decreasing, IA2 decreasing. Later onwards, IA1 increases and this side current increases. This side current. First it is decreasing like this, and again it will be increases. As excitation changes, variation of current is a V curve. And similarly, draw the power factor. What is going to be happen? Power factor with minimum excitation. E4, I am taking minimum excitation E4, maximum E1 in this diagram. So with minimum E4 excitation, see IA4 angle is more, na? Phi 4 is more, angle is more. When angle is more means cos phi is less. Angle between V and IA, power factor is less, angle is more, V to IA4 angle is more. So therefore what should be the power factor? Power factor is less, power factor is small, power factor less. And again increase excitation, E3. When excitation increases, angle between V and IA3 reduced. Phi reduced, power factor angle reduced means cos phi will increase. Cos phi will increase. Power factor increases. Similarly, again increase the E2 excitation. Now we are normalizing E2. Then IA2, what is phi? Phi is equal to 0. Phi 0 means power factor 1, UPF. For IA2, UPF. Power factor is UPF. Maximum. UPF is maximum, na? Yes, maximum. Similarly, still increase excitation E1. Then angle is again increasing. First this side, left side you observe IA4, phi maximum. But IA2, phi decreasing. IA3 decreasing. IA2, 0. Still increase, current is increasing in this direction. Right side it is increasing. But right side angle is again increasing. The angle increases, power factor will reduce. Okay? Power factor will reduce. So therefore, what is this? This will be the inverted V curve. This is an inverted V curve. Power factor is an inverted V curve. Current is a V curve. Okay? And where current is minimum? Normal excitation. Current is minimum for normal excitation. Which is normal excitation? E2. Because E2 cos delta 2 is equal to V, normal excitation. Right? Yeah. Similarly, if you draw the variation of delta, how it is? Tell me. Just observe delta variation with respect to field current. Delta also varying with respect to excitation. Delta. Can you draw the delta? How it is? When excitation increases, delta decreasing or increasing? When excitation increases, delta, is it decreasing or increasing? Excitation increases, delta is decreasing. E4 means delta 4 is maximum, na? Yes, delta 4 is maximum. Right? Delta 4 is maximum. This is delta 4. Delta 4 is maximum. Is an angle between V and E, delta 4 maximum. When excitation minimum, delta 4 maximum. When excitation increases E3, this angle is reducing, delta 3 decreasing. When excitation increases, delta decreases. Excitation increases, delta decreases. Correct? As excitation increases, E vector coming closer to V vector. So therefore, delta variation is like this. The delta variation on this, delta decreasing. Delta decreases. Delta will reduce. Right? Yeah. So let me draw these conclusions in the next page, and after that we will see all varieties of objective questions on this topic. Objective questions. So I hope this diagram is clear. Based on that, I am getting the V curves and inverted V curves of synchronous generator. So V and inverted V curves. So V and inverted V curves of V and inverted V. Inverted V curves. V curves and inverted V. V curves, V and inverted V. Inverted V. That is nothing but this is inverted V, na? Inverted V curves. V and inverted V curves. Let me draw clearly here the V and inverted V curves. This is excitation, IF, current and power factor. Current and power factor. Variation of current. Variation of current is V curve. Variation of current is V curve. Is a V curve, and power factor is inverted V curve. The V curve, power factor is going to be inverted V curve. This is IA, this is power factor. Power factor. So what is this? This is said to be normal excitation, and this is under excitation. This is under excitation. Okay, and this is over excitation. This is normal excitation. Yeah, normal excitation. Now for normal excitation, what is the power factors for normal excitation? Power factors. For normal excitation, power factors are, power factor is normal excitation. Power factor is UPF. Under excitation, power factor is, for under excitation, power factor is leading power factor. Leading power factor. Over excitation, power factor is lagging power factor. Normal excitation, power factor is UPF. Normal excitation, power factor UPF. And for under excitation, what happened? Q absorb. For under excitation, Q will absorb. Over excitation, Q will deliver. And for normal excitation, what about Q? Q is equal to 0. For normal excitation, Q is 0. Q0. Similarly, to draw the variation of delta with respect to excitation, this is IF. IF is nothing but excitation. With respect to excitation, this is the delta. So delta variation is decreases. Delta decreases. Okay. So these are the important conclusions. Yeah. So all your questions, objective questions, any objective questions are giving based on these concepts only. Okay. So now I will give the objective questions. Let me give the objective questions. See, an alternator operating on the bus bar. The question is like this: an alternator is operating on the bus bar. Okay, are you ready? Have taken? Yes. The power factor. First of all, I have got what is power factor. Power factor is nothing but angle between V and IA. Alternator will deliver the current, na? In this diagram, it is delivering the current. Current delivering or not? Yes, it is delivering the current. IA is passing through this. IA. Then what is the angle between this V and IA? That is only a matter. IA cos phi may be deliver, IA sin phi may be observed, but resultant current, angle between V and IA, that is a power factor. So lagging power factor means don't think we are not connecting inductive loads. When leading power factor means we are not connecting. Loads are somewhere, but I can control power factor in the machine itself. My machine can operate any desired power factor, irrespective of loads. I can supply active power. Okay. If you want to deliver reactive power also, you have to over-excite it. At that time, it will operate lagging power factor. So it is applying the reactive power to the lagging loads. If under-excited, it will also absorb. From where it will absorb the reactive power? Remaining machines. Remaining alternates are there, it will take it. Okay. Mainly, for your examination point of view, the questions are, yeah, I'm giving the question. See, an alternator is operating on the bus bar. An alternator is operating on the bus bar. Bus bar at leading power factor. At leading power factor with constant mechanical power input. Constant mechanical power input or constant prime mover input, or constant load also. You can say or constant load, all meanings are same. Or constant load. It's operating at leading power factor with constant load. If the excitation is increases, now if the excitation increases, then power factor what happened? Then what is the power factor? Power factor what happened? And current what happened? Okay. Delta what happened? Q what happened? Okay. Yeah. P what happened? What about E? What about V? What about F? What about N? What about T? Electromagnetic. And all they will be increases or decreases. Okay. This I can write a side. Okay. One by one. I will give the space to answer that. Power factor what happened? Current what happened? Okay. Delta what happened? Q what happened? And P what happened? E what happened? V what happened? Increases or decreases? That you have to say. N, what about N? And what about electromagnetic torque? They are increases or decreases? Power factor increases or decreases? Current increases or decreases? Delta increases or decreases? Q also increases or decreases? So this type of question can be answered very easily from this diagram. See, dear students, you should know this is leading side. Na? Where is leading side? Leading side means left side, leading side. Your machine is operating at some particular leading power factor. You take here. For example, you are operating here. Your machine is operating at this condition. Okay? Your machine is at this point. Now, when excitation increases, say, what is happening? When excitation increases, current is increasing, power factor is increasing. But what about current? Current is decreasing. So power factor is increasing. IA is decreasing. What about delta? Delta is decreasing. Q will be decreases. Why? Because remember that always Q always inversely proportional to power factor. This is always valid. Q inversely proportional to power factor. Here power factor is increasing, na Q will be decreases. Why? Because you are coming towards the Q0. See, you are under excitation, you are coming towards the normal excitation. When normal excitation means what is happening? Q is going to be reduced to 0. Yes. Your normal under excitation is not sufficient for you. And when excitation increases, absorption, reactive power is absorbing, that absorption decreases. You are increasing excitation, you are increasing the field current. Necessity of reactive power decreases. You are reaching towards the Q0. Q0. Okay. Q decreases. Because here power factor increasing, Q decreases. Yeah. Then what happened? The power constant. Active power is constant only. Active power is constant. Why? Mechanical power constant. Yeah. Throughout this discussion, heading is important. Constant mechanical power input. We are changing only excitation. Okay. Yes. So mechanical power constant, active power constant. What about E? E increasing. Excitation increase in E increase. What about V? V remains constant. V remains constant. Who will do that? Reactive power will take care. It will magnetize or demagnetize such that V terminal voltage is constant. What about speed? Speed remains constant. Speed remains constant. Alternator operating the bus bar, speed constant. Because prime mover torque constant, electromagnetic torque constant, speed constant only. If you change excitation, there will be no change of its speed. Rotate constant. TEM, electromagnetic torque also constant. Why? Why? Because mechanical power is constant, since P constant. Since P constant means electromagnetic torque also constant. Right? Okay. Now, let me do another question. Another question. See. An alternator. Question is, an alternator is operating on the bus bar. Operating on the bus bar. Bus bar at lagging power factor. Lagging power factor with constant mechanical power input. With constant mechanical power input. With constant mechanical power input or constant prime mover input or constant fuel input or constant steam input. All meanings are same. Examiner can use any words. Constant steam input or constant torque also. Constant prime mover torque. All meanings are same. Constant prime mover torque. Okay. Lagging power factor with constant mechanical power input. Otherwise, constant power input means all they will be valid. Fuel input constant. Steam input, water input, everything constant. Constant mechanical power input. Okay. Now, if the excitation increases, then excitation increases, then power factor what happened, current what happened, delta what happened, Q what happened, P what happened, E what happened, what about V, what about F, what about N, what about TEM? Torque. Machine is operating at lagging power factor with constant mechanical power input. Constant mechanical power input. But if the excitation is increased, So with that, this is V curves, inverted V curves, na? Yes, IA and power factor, excitation. You know that V curve and inverted V curve. Inverted V curve. This is IA, this is the power factor. IA power factor and this is the delta. Okay, where you are at lagging power factor. This is lagging power factor this side, na? Yes. So you are at lagging power factor means lagging power factor will be on this side. This side will be lagging power factor. So You are here, say, you just select a point, select a point. On this, when excitation increases, what happened? Power factor decreases. Power factor decreases, but current is increases. Current is increases. Okay. Power factor decreases. Current increases. Delta will be, this is the variation of delta, no? Yes. What is happening delta in this condition? When excitation increases, delta decreases. They are increasing, delta will be decreases. Delta decreases. Q will be delivering increases. Delivering. Q delivering increases. Delivering increases. Earlier, absorption decreases. Earlier question I have given, it is coming toward the under excitation was absorbing, but when excitation increases, absorption will reduce. But here already it is lagging side, already delivering, Q already delivering. And when it is more delivering, this is Q, Q0, it is going away from this Q. More delivering increases. P constant. What about E? E increases. V constant only. V constant. F always constant, frequency constant. Speed also constant. EM increases. Electromagnetic torque also constant. EM also constant. Okay? Yeah. Constant. Remember that always. Q always inversely proportional to power factor. You can remember blindly. Power factor is decreases means Q increases. Q delivering increases. Because already it is delivering side. Already delivering. When excitation increases, still more delivering. Whereas earlier question I have given, Q absorption decreasing. Your absorption is decreasing. Because it is already absorbing, but you are coming towards the UPF. When excitation increases, necessity of reactive power decreases. You absorbing, but absorption decreases, and finally it will come to zero. Yeah. Question may be asked like this, dear students. The question may be asked. Another question I will give. See. Next question is, an alternator operating on the bus bar. At leading power factor. Operating at leading power factor with constant mechanical power input. Or constant load. Okay, constant load. If the excitation increases, then A bit. IA increases, power factor decreases. IA increases, power factor decreases, B bit. IA decreases, power factor increases, C bit. IA increases to maximum value. IA decreases to minimum value. IA decreases to minimum value. Later onwards increases. And power factor increases to maximum value. Later onwards decreases. decreases. Similarly, D bit. IA increases to maximum value, comma, later onwards decreases, and power factor decreases to minimum value, later onwards increases. This is also your previous GATE examination question. Later onwards increases. Later onwards increases. Yeah. So tell me, what is the answer for this? Okay. Answer is the answer B and C. D. Yeah. Taken? Draw the diagram and then come to the answer. See here, power factor and current, na? Yes, is IA and power factor. IF weaker, inverted weaker. IA. So where you are, this is leading side, leading power factor, this is lagging. Lagging, na? Yes. You are at leading. Now you are at leading. For leading power factor, see here, for leading power factor here, and when excitation increases, what is happening? Power factor increases to maximum value, later onwards decreases. Current is decreases to minimum value, later onwards increases. So therefore, what is your answer? Answer will be current decreases to minimum value, later onwards increases. Power factor increases to maximum value, later onwards. Answer is C. If C is not there, what is your answer? If C option is not there, what is your answer? Your answer will be current decreases and power factor increases. That's all. If C option is not there, then I will go for B. If C is not there, actually answer is C. Okay. If C is not there, then answer would be B. Correct? But exact answer is there, na? Exact answer is there. It is increases and later onwards decreases. Now, how long you will increase excitation means that is a matter. The excitation keep on increases, you are at under excitation actually. Leading side means under excitation. And when still excitation increases, you will go to the normal excitation, then UPF, still increase excitation, you will come to the over excitation also. Okay. Then based on the options, you have to choose your answer. Similarly, I will give another question. Okay. So DRDO examination question I am going to give. You have taken this? Yes. DRDO 2010 examination question is like this. An alternator operating. An alternator operating on the bus bar. With constant mechanical power input, with constant prime mover input, constant prime mover input, okay, or constant load. An alternator operating the bus bar with constant prime mover input or constant load. If the excitation decreases, the excitation decreases. The excitation decreases. Excitation decreases. Then excitation decreases. Then A bit. Power factor increases. Current decreases. B bit. Power factor decreases. IA increases. C bit. E decreases. Delta increases. And D bit. E increases. Delta decreases. Yeah. So answer, your answer. Fine. Okay. So answer is, yeah, what is the answer? Tell me. Answer also C. Answer is C. Exactly correct. You are correct. In this, he has not given any power factor. So earlier examination, earlier questions was given power factor. Is it operating lagging power factor, leading power factor? It is given earlier questions. But here he is not giving any power factor. Na? Is related to question is related to Vickers, inverted Vickers, fine. But is it operating leading lagging power factor? Means it is not given. If you take lagging side, your answer will be different. Leading side, answer will be different. Because current and power factor, you cannot decide. Power factor increases, decreases, we cannot decide. But excitation, E proportional to excitation, delta inversely proportional to excitation. That is known. Lagging or leading side, C. Coming to this is power factor and current, IA and power factor, delta is decreasing. This is normal excitation, this is normal excitation, this is under excitation, over excitation. But whereas if you take current it would be different. If you take lagging side or leading side, current is different. So in this question, power factor is not mentioned. Power factor is not mentioned. Whether it is leading or lagging, not mentioned. Therefore, we are not sure about IA and power factor. Whether increases or decreases. Whether they are increases or decreases, we cannot decide. Okay? Whether increases, it cannot be decided. Cannot be decided. But excitation, E is always proportional to field current, but delta always inversely proportional to field current. This is fixed. Both for lagging and also leading power factor. So this is normal excitation. If you take here also, as excitation decreases, what is happening? Delta increasing. Even if you take here also under excitation, when excitation decreases, then also delta will be increases. Both lagging power factor, leading power factor, they are valid. These are valid. both for valid, both for lagging power factors and leading power factors. Lagging power factors and leading power. This is valid. Lagging and leading power factors valid. Okay. So your answer will be when excitation decreases means when excitation is decreases means E decreasing, delta increasing. Answer will be C. C. Therefore, answer is C. Okay. Yeah. Now, then similarly, see next question. Taken na? This over? Yes. Coming to the next question. An alternator operating on the bus bar. Operating on the bus bar. Bus bar with a constant mechanical power input. With constant mechanical power input. Constant mechanical power input. Increase in excitation causes. Increase in its excitation causes. Increase in its excitation causes. Increase in its armature current. Increase in its armature current. Increase in its armature current. Then increase in its armature current. Then the machine will A bit deliver the Q. Deliver Q, operate at lagging power factor, operate at leading power factor, B bit. Observe the Q, operated lagging power factor, C bit. Deliver the Q, observe Q and operated leading power factor, and now deliver Q, operated lagging power factor, D bit. Observe the Q, operated leading power factor. So what is your answer? Okay, what is your answer? Increase in excitation causes. This is IA power factor, normal excitation, under excitation, over excitation. That is delta. Okay. Now delta is not required here. Increase in excitation. But what about here? Here Q will be deliver, observe. Q deliver. This power factor, we know what is the power factor? Leading, and this is lagging power factor, lagging. So increase in excitation causes, and where you are, increase in excitation causes increase in armature current. So you are on lagging side. Excitation increases means this is lagging side. Lagging side, Q will be deliver, na? Q deliver, operated lagging power factor. Machine will deliver the reactive power and operate at lagging power factor. Okay. Yes. Fine. So questions will be like this. All the questions will be like this. And important thing here to remember, which is weaker, which is inverted weaker. You know, examinations also question will be, he will give curve. When curve is given, which is weaker, which is inverted weaker, you have to identify. You have to identify. Okay, you have to identify. Okay. Yeah. See, you ready? Yes, yes. I will come to your doubts. Just a minute. People are raising hands. Okay. See, examinations, which is weaker, which is inverted weaker is important. Right now, when you are seeing now, it is clear. Okay. You can say yes. It is, yeah. It is weaker, inverted weaker, so you can remember. But after going to examination, there will be a confusion between which is weaker, which is inverted weaker. Is IA is weaker or inverted weaker? Power factor is weaker or inverted weaker? This is the confusion. If you confuse there, whatever all discussion will wrong. Whatever we have discussed, all the things will be wrong. And I will give you a tip to remember all these things. You can easily remember all the things. See how you can remember. Listen. Important thing is, for normal excitation, power factor is UPF. If you remember that point, it will be enough. This is normal excitation. Power factor is UPF. Only remember that point. This is normal excitation. Power factor, what is power factor? UPF. And that UPF is maximum, na? Maximum. Maximum. That will be the power factor. That's all. Normal excitation. Important point is, for normal excitation, power factor is UPF. UPF. That is maximum. Which is maximum? Which is maximum? Maximum. But where normal excitation? Some students will say where normal excitation will be in middle. Correct? Normal excitation in middle. In middle it is maximum. Ante inverted weaker. In middle is maximum. Middle maximum. So that side, this side it is less. Okay? That side, this side it is less. Normal excitation power factor is UPF. Which is maximum. Okay? So normal excitation is at middle. At middle. Therefore, power factor is maximum. Power factor is maximum at middle. Middle. And like this. Power factor is maximum. At middle it is maximum means that side decreases only. Na? Both side it is decreases. Correct? This is a middle. Normal excitation. Power factor is maximum. So just to remember that point. Whenever you are getting confusing, say, there is no confusion, nothing. Normal excitation power factor UPF. If you remember that point, now you can forget about all the conclusions. All the phasor diagram is not required. We have drawn the phasor diagram, then we have got weakers, inverted weakers. Na? Yes. Now you nothing to worry. When you are doing the problems also, all the conclusions will be valid. All the conclusions are valid. I have given objective question, na? Numerical values also. So your conclusions will be satisfied with numerical values also. So here only one important thing. For normal excitation power factor is UPF. Normal excitation where it is middle. So at the middle power factor is maximum. And that side it is decreases. On both sides it is decreases. It is an inverted weaker. So when power factor is inverted weaker means current is weaker. Current automatically weaker. Anyhow, delta is decreasing. Delta decreasing. Okay. So this is about the effect of change in excitation. Right? Yeah. So now next topic we will see after the break. But any doubts are there in this, please raise your hands. Just for 5 minutes doubts. Others also please stay. and others, maybe some people may be getting a doubt, the same doubts maybe others also may be getting. After 5 minutes, we'll go for break. After doubt session, we'll go for break. And next topic, we will complete. So with that, alternative topics will be completed. Our 6th chapter will be completed. Then we will go for 7th chapter. After the break, we are going to start. First, the leftover topic of synchronous generator, alternative topic, effect of change in mechanical power input. We will complete that. It may take around some 40 minutes. After that, we will start our synchronous motors. Okay. Yeah. Yeah, tell me your unmuting. Okay. Yeah.
Sir, in this the, phasor diagram, sir, that load effect of change in excitation.
I'm unmuting first of all the people. Okay. Phasor diagram.
That how that IA is drawn only, I have doubt, sir. This IA, how it is?
IA, this is locus of IA is a straight line. Locus, this is locus, na? This must be
Yes,
locus. IA, tip of IA should be false along this. Then only IA cos phi will be constant. For example, IA1 cos phi is equal to IA2, correct? IA4 cos phi also equal to IA2, na?
Yes, sir.
IA2 cos phi also equal to IA2. And power factor is 1. So it has to fall on this. This is the tip of IA. IA vector will be whatever the magnitude, but IA tip must be aligned in this. Then IA cos phi will be maintained constant. E sin delta is constant, means this is the locus of E. That's the reason I have it.
Okay. Sir, my doubt is how we are drawing IA when this is when we are reducing the excitation, sir.
First, okay, we are reducing E. Join V to E first. You are drawing E, na? Then join V to E. Okay, that will drop. When that is drop, means current will be perpendicular. Current will be, how it is, current will be perpendicular to that. Na? This is drop, say. Then how current will be perpendicular? Okay, sir. IA axis I am drawing. Then I am drawing IA. First you draw the IA axis. That's what I told. IA. And everywhere I have given IA axis leads the current IA. I have given statement already.
Yes, sir.
Drop leads the current. You can see every diagram, it is valid. Not only here, any circuit, any wave, any vector diagram you see, drop, reactance drop leads current. Okay, sir. Here that logic why I couldn't get us. Usually whenever we draw this phasor diagram, there used to be an IARA component. From there we used to draw perpendicular IA axis. Yes. First you will draw the IA, then you will draw the drop. But here I am going reverse way. First I am drawing the drop, then I am drawing the current. So whatever IA we are drawing, that like if you extend it, that must be perpendicular to IA axis. Yes, exactly. All right, sir. Thank you, sir. Right.
Hello, sir.
Hello. Yeah, tell me.
Sir, slide number 9.
Slide number 9, huh?
Okay. Yes, sir.
Yeah.
Sir, in this question, they are saying that leading power factor. So, sir, we should consider only up to the region where there is leading power factor.
Yes.
So, sir, then option should be B.
No, ma. That's what I told. If option C is not there, B. I don't know how long you can increase excitation means. If it is keep on increases, say, then it will increases, decreases. Of course, you may be confusing with this type of question. This question, no? Okay. These questions.
Sir, if we keep on increasing, then it will go to lagging.
Yeah. Tell me. You are at leading side. For example, if you take, it is given leading power factor, na? Where it is given leading power factor is given. I am continuing with this leading power factor. Leading power factor, you are here, okay? And when excitation increases, definitely power factor increases to UPF. Still you continue increasing, it will go to lagging also. You are under excitation, okay?
Yes.
But when excitation keep on increases, for one particular point, you will come to the normal excitation. Still you increase, you will go to the over excitation. If the question option, based on the options, you have to respond. If C option is not there, what is your option? Definitely I will go for B. That's what I have given.
Sir.
But correct answer is there, na?
Sir, then,
how much it is increased? If he is mentioning only, if this question may be given like this, listen. If my question may be, alternator is operating under leading power factor. Alternator is operating only under leading power factor. When excitation increases, current decreases. Only as long as you take leading side, he has to give question in the question if it is mentioned. Alternator always operate only at leading power factor. leading power factor. When excitation increases, what happened? Current decreases, power factor increases. Conditionally, he will give the question clearly. But what I am saying, it is operating at leading power factor, okay. Excitation increases, it will go to over excitation also. Right now, under excitation. Keep on increases. Based on the options, we have to respond. Which is 100% correct answer means C will be. C is not there, B will be, then it will be correct.
Then, sir, in the next question also, we should consider that excitation is decreasing to the left side.
No, ma. Yeah, wherever excitation decreases, it is given. In this question, you see an alternator operating on the bus bar with constant prime or input. He has not given power factor.
Yes, sir.
So therefore, you cannot say power factor, what is happening, which side you can take, lagging or leading. If you take leading side, you will get one answer. Lagging side, if you take, you will get another answer. Leading side, if you take, answer one answer. The lagging side, another answer. Two options you will get. Which
Sir,
is not
leading
correct.
side,
Huh?
sir, leading side excitation will always be less than lagging side. So we
Huh?
can take.
Okay. No, ma. If the he is not mentioning where the power factor is. Excitation is decreases, that's all. Okay, if you take this side, see, if you take this side, when excitation is decreases, what is happening? Current is decreasing, na?
IA decreasing.
Power factor
Yes, sir.
increasing. Which option?
Increase.
Your option is, which option is correct? A correct. Okay. If you take this side, what happened?
Yes, sir.
Power factor, current increases, power factor,
IA
current
Decrease.
increases, power factor decreases.
decreases.
My answer then B. Only one option you have to choose. Which option you can choose?
Okay, sir.
So therefore, that's the reason current we cannot decide.
C. Yes, sir.
But C correct. You
Okay,
take
sir.
lagging side, leading side also. E proportional to excitation. Delta proportion, inversely proportional to excitation. That's the reason C will be correct. Any power factor you take. Okay. Right.
Okay,
Next.
sir.
Hello.
Thank you, sir.
Thank you. Next, anyone? Hello. 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 Hello.
Sir, my doubt is clear.
Yeah. Clear. Very good. Okay. So now let us take break. Break for 20 minutes. Class will start. Okay. Yeah. So now, second case, let us see effect of change in prime mover input. So alternative will have two inputs. Already we have seen change in excitation. Now if you change mechanical power input, what is going to be happen? So next heading is effect of change in mechanical power input. Okay. Yeah. Effect of change in mechanical power input. Case 2. Effect of change in mechanical power input. Mechanical power input or prime mover input, no? Or fuel input, all meanings are same. So effect of change in mechanical power input. Mechanical power input and excitation is kept constant. Excitation is kept constant. Excitation is kept constant. Excitation is constant. So for this, alternator is connected on the bus bar. Excitation kept constant, but we are going to change the mechanical power input, P mechanical. Based on the field current, say it is north pole, south pole. EMF is generated in the armature winding, that is E. V always constant. Whatever you do, V is not going to change. V constant. Terminal voltage is constant. Okay. Yeah. And here, field current also kept constant. IF we are keeping constant. When field current is constant means IF. Excitation constant. Therefore, E also constant. E also constant. But mechanical power input, P mechanical is changed. Mechanical power input we are changing. The prime mover torque we are changing. TPM we are changing. Prime mover torque has changed. But omega always constant, we are going to see. P mechanical changes. When P mechanical changes, what about P electrical? P electrical also will change. P electrical. That also will change. Electrical power will change. And what about reactive power? Tell me. So when we are changing mechanical power, energy neither created nor destroyed, according to energy conservation, you are giving mechanical power. It will convert equivalent electrical power, and that will be given to the bus bar. I'm not showing here. You can understand. Machine is fed and right side loads are there. The power will goes to the load. It is supplying the load. Excitation is kept constant. What happened? Q. Excitation constant means is the Q constant or changes? Q also changes. Q is not constant. When excitation constant, Q is not constant. I am going to show that. because delta changes, Q also changes. You will come across. Under this, the important thing is see, power is equal to EV by XCS sin delta. Power is equal to EV by XCS sin delta, but V and XS anyhow constant always. V XS constant, E also constant. Why E constant? Since excitation is constant. Excitation is constant, that's the reason E also constant. E constant. Then what is P? P is proportional to only sine delta. P is proportional to only sine delta. Because all other things are constant. Na? E, V, XS, all these are constant. E, V, XS, all these three components are constant. Then power is proportional to only E sine delta. E sine delta. So therefore, when mechanical power input increases, therefore, as P mechanical increases, P electrical also increase. When P mechanical increases, then P electrical increases. And when P electrical increases, sine delta will increase. Sine delta will increase, then load increase. Sine delta increases and delta also will increase. P increases, let me call load also increases. Load also increases. Load increases. It will take more load. Sine delta increases. Delta also increases. Delta also increases. As your mechanical power increases, electrical power, load, delta will also increases. Delta changes. Okay. Why? Because you are applying more prime mover torque. More prime mover torque means E. You are pushing prime mover. You are pushing means rotor poles leads. When rotor poles leads, E also will leads. E also will leads. Right? E magnitude constant only. E magnitude constant. But how? What is going to be happen? This is V, say for example V, and this is E, say E. But E will be shifted. E delta will increase. Sorry. E magnitude same, but locus of E is a circle. Na? E is, this is E. Delta increases. What is going to be happen? Delta has to increase. Delta increases means locus of E is a circle. E shifted. E will shift. As load increases, delta increases. Delta increases. Okay. What is delta? Delta is nothing but angle between this. Na? Delta is the, this is delta 1. This is delta 1, delta 2, delta 3, delta changes. Okay. And another relation, we know E is equal to what? V plus J into IA XS. That is always valid. Always valid. And Q is equal to V by XCS. E cos delta minus V. E cos delta minus V. These relations always exist. Okay. So important thing here, as load increases, E will be, as prime mover input increases, delta increases because we are pushing the prime mover torque. Rotor poles leads. And rotor poles leads means rotor MMF leads. Then rotor MMF leads, E vector will leads. E leads the V. Delta increases. Therefore, locus of E is a circle. Magnitude of E is constant. Magnitude of E is constant. Delta increases. Delta increases means E will shift. So let us draw the phasor diagram corresponding to that. The phasor diagram is so this is a V. Okay. The V is IA XCS drop. This is E. E. J into IAXA. This is E. So first I am drawing the J into IAXS. Then current will be perpendicular to drop. IA. That IA is perpendicular to this drop. This is delta 1. For example, you take this is delta 1. Delta 1 is related to E. But delta has to increase. Na? As load increases, delta has to increase. As load increases, E should be more leading. Because rotor poles leads, E should be more leading. E is more leading means E is more leading. Therefore, locus of E is a, this is locus of E. Locus of E is a circle. E magnitude same. Locus of E is a circle. How long that will be changes up to delta 90 degrees. Up to delta 90 degrees. Okay, delta, here it is delta, first delta E. Next E will come to here after some time in the sense when prime mover input increases. This is the E angle increase. Still increases. This is E. Similarly, E. Like, yeah. Delta increasing, na? Delta is increasing. Delta is increasing. Delta 1, delta 2, delta 3. Okay. Delta. What is this? This is delta 1. This is delta 2. Delta 3 increased. Like delta 4. Delta 5. Delta 2. Delta 3. Delta 4. Delta increasing. When delta increasing means E vector should be more leading. Okay. Therefore, when prime mover input increases, for one particular prime mover, delta 1 still increase, delta shifted. E should be more leading, na? E should be more leading. So E will be shifter. E will be shifting. Delta has to increase means locus of E is yes. E magnitude same, but delta changing. Now, then draw the V to E. Draw V and E. That is nothing but drop, no? Draw V and E. That is a drop. Let me draw the drop phasor. Drop. This is IAXS, IA1XS. IA1XS. Join V to E. That is J into IA to XS. J into IA to XS. Now this is J into IA3XS. J into IA3XS. This is J into IA4XS. J into IA4XS. J into IA5XS. This is J into IA6 into XS. These are the drop vectors. Drop vectors from V to E. Simply join V to E. So this is J into IA1XS, J into IA2XS. Now draw the current vector. Once you know the drop vector, current vector is perpendicular. So first I am drawing the drop. Drop in the sense join V to E, that is a drop. Join V to E, that is a drop. Then draw the current perpendicular to the drop. The current will be, drop is perpendicular to the current. Or current is perpendicular to the drop. Now draw the current. The first one is, this is IA1, yes, IA1. That is related to delta 1. Similarly, this is IA to XS is there, na? IA to XS, if you extend like this, then what is going to happen? This will be the IA2. This is IA2. IA2. That means it is said to be perpendicular to IA to XS, perpendicular to IA to XS. So this is IA2. This is IA2. Okay. Now IA3. IA3 XS is horizontal, na? IA3 XS horizontal. Therefore, IA3 is perpendicular. Drop is horizontal, current is perpendicular. So IA3 is vertical. This is IA3. 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 This is IA2. IA3 and IA4. IA4 is perpendicular to this drop. So therefore, this will be the IA4. IA4. IA5 is perpendicular to this. This is IA5. IA5. IA6 is perpendicular to this. Therefore, this is IA6. 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 Okay. Current magnitude is keep on changing. Now you see power factor angle, power factor angles. Power factor also changing. Power factor also changing. Right? If you take this is phi 1, power factor angle phi 1. This is phi 2. Phi 2 lagging. Phi 3 0. What about this? This is phi 4. Phi 4. This is phi 5. Power factor angle. Like that phi 6. Power factor is angle between V and IA. V and IA. Okay. So, in this, your observation is current magnitude is changing, delta is changing, okay, delta is changing, power factor is changing, reactive power also will change, reactive power also will change. Now my question for you is, I have kept load is constant, na? Mechanical power input is constant. I kept mechanical power is constant. When mechanical power is constant, mechanical power input changes. Excitation is kept constant. Dear students, the question is like this. Listen. Excitation is kept constant. When excitation is constant, why power factor is changing? Why it is operating at lagging power factor and also leading power factor? Okay. Excitation is kept constant. Sound like a number. Excitation go alert cheyakandi. Hello. Okay. See, excitation is kept constant, na? Yes. And when excitation is constant means, why power factor is changing here? Power factor why changing? IA1 lagging, IA2 lagging, IA3 leading. IA3 UPF, IA4 leading. Why it is going lagging and also why it is going leading side? Power factor. Though excitation is constant. When power factor changes, reactive power also going to be changes. That also we will observe. Right? Let us see. Why lagging or leading power factor means mainly power factor is depends upon, power factor is depends upon E cos delta. Though E is constant, but E cos delta is changing. Power factor is said to be E cos delta. Is it greater than or less than or equal to V? That is deciding the power factor. That decides the power factor. And Q also, reactive power is equal to what? V by XCS. E cos delta minus V. In this, E constant A. But when delta changes, what is going to be happen? E cos delta changes, na? Yes. And as long as if E cos delta greater than V, it is said to be lagging power factor. When E cos delta less than V, leading power factor. E cos delta is equal to V, UPF. And similarly, and when delta changing, as delta changes, Q also will change. Though E constant. Right? Yeah. E constant. Now, see here how that E cos delta changing. Why power factor changing means E cos delta changing. Let me show that. E cos delta. Yeah. E cos delta. I just want to use another some color, light color. Okay. See, this is E cos delta. This is E cos delta, na? Yeah. The first one, E cos delta. E cos delta 1. E cos delta 1 is greater than V. When E cos delta greater than V means what will happen? It is said to be leading power factor, lagging power factor. E cos delta. Just a minute. Let me draw clearly because it will be helpful. This is E cos delta vector. E cos delta greater than V. E cos delta 1 greater than V means what is the power factor? Your power factor will be lagging power factor. And similarly, E cos delta 2, if you say, this is E cos delta 2. E cos delta 2 is greater than V. Greater than V means that is also lagging power factor. Similarly, this if you take E cos delta 3. E cos delta 3 is equal to V. That is said to be UPF, unity power factor, UPF. And for this, if you take, this is E cos delta 4. E cos delta 4 is less than V. Less than V means it is operated leading power factor. Similarly, like E cos delta 4, delta 5 is also less than V. Then also it is leading power factor. Okay. The power factor, operating power factor is depends upon the whether E cos delta greater than V or less than V. That is deciding factor. Correct? Yes. The power factor is depends on the leading, lagging. Right? Taken. But as long as E cos delta greater than V, lagging. E cos delta less than V, leading. Delta changing, na? Yes. E same. So, E cos delta as long as E cos delta greater than V, lagging power factor. E cos delta less than V, leading power factor. Both are equal, UPF. But in this, delta is varying, na? That's the reason E cos delta may vary. And even Q also will changing, na? Q also changing. Q is equal to what? V by XCS E cos delta minus V. So as when delta changes, Q also will change. Q also will change. Q magnet, why students will express a doubt. When mechanical power input constant, active power constant, correct? That is pakka. But when excitation changes, reactive power is not constant. When excitation changes, when excitation constant also, reactive power is not constant, varies. Why? Because power constant, delta varying. When primary input changes, delta varying. E constant, E cos delta. Whenever you are seeing reactive power, you have to see with this equation. Okay? Yeah. Now, so for making the conclusion, standardization conclusion here, on this, to discuss objective questions, let me divide that into two regions. Based on the current, I can divide like this. This is said to be lagging power factor region. This is said to be lagging power factor region. Current, lagging power factor region. Lagging power factor region. Current is lagging side, left, right side. And this is said to be leading power factor region. Leading power factor region. Leading power factor region. Okay. Leading and lagging. Currents, which is IA1, IA2 lagging power factor, but IA4, IA5, IA6 leading power factors. Leading power factors. So leading power factor region, lagging power factor region. Now under this, for making the conclusions on leading side and lagging side, what is going to happen? Leading side, lagging side. Let me write here. See, your observation is when machine is operating under lagging side. When machine is operating under lagging side, dear students, see. This is IA1, phi 1. IA1 is phi 1. But when prime mover input increases or load increases, IA2 coming closer to V. Okay, what is happening? Phi means IA1 is there na phi 1. But when prime mover input increases or mechanical power input increases, IA2 means angle is reduced. Angle is reduced means power factor increase. And still increases IA3. Phi decreases to 0. UPF. Mean to say, see my hand. So this is V vector, say. This is V vector, current vector. Current vector, as load increases, E shifting counterclockwise direction, then IA also shifting in counterclockwise direction. Angle is shifting, na? When load increases, delta has to increase. In which direction delta shifting? IA also shifting in the same direction. The earlier IA1 is here, but as load increases, IA2, angle is reduced. Angle between E and V reduced. So power factor increases. Can I say as load increases, power factor increases? Am I right? As load increases, power factor increases. Therefore, on this side, I can say power factor is proportional to load. Power factor is proportional to mechanical power input. That mechanical power input is proportional to load. So power factor is proportional to load on lagging side. But if you see left side, leading side, IA4. And when load increases, E5 it will go. Then IA5, angle increases. Then IA6, angle increases. When angle increases, power factor decreasing. So when load increases, E shift up, but IA also shifting. IA is going away from the V phasor. Therefore, phi increases, power factor decreases. Therefore, as prime mover input increases, power factor decreases. Inversely proportional. This side, power factor is inversely proportional to mechanical power input. Inversely proportional to mechanical power input, or inversely proportional to load. Next, what about current? Reactive power. Directly I can say reactive power. What is happening? Q inversely proportional to power factor. So that's the reason Q will be Q delivering or absorbing lagging side Q delivering, but that Q delivering is inversely proportional to mechanical power input are inversely proportional to load, because power factor and Q inversely proportional. Both are inversely proportional. That's the reason directly I can say power factor proportional means Q inversely proportional. And what about here? Q will be proportional. Q absorbing. Q absorption is proportional to mechanical power input, proportional to load. I will write other side in the next page. I will give you a table for explanation. I am writing here. Okay. Yes. But what happened? Current, tell me. Current is increasing on both sides. Lagging side also current is increasing. Leading also current is keep on increases. Because when load increases, delta increasing. Primary input increases, load increases, delta increasing. Angle between V and IA increasing. The phasor difference. See, phasor difference between V and IE, vector difference of the voltage, potential difference increases. Then current increases. Lagging side also IA1, IA2 increasing, IA3, IA4, IA, they are increasing. Right? Yes. So IA increases on both sides. IA proportional to on both sides. IA is proportional to load, primary input, mechanical power input. IA is proportional to mechanical power input. Load say. And this side also IA proportional to load only. IA is proportional to load only. Fine? Yeah. Even you can find how IA increases means drop. What is happening? Drop. IA1X is drop. IA2X is drop. IA3X is drop. Drop increasing. IAXS increases, but X is constant. Why drop increasing? Why drop increases? Because current increases. Why current increases? Potential difference. V to E angle increases, current increases. Delta is responsible for the current flow. I told. When delta is more, current flow is more. When delta means angle between V and E increases, then drop between V and E. You join V to E tip, drop increases, then current definitely increases. Right? Yes. So let me write, this is in the next page. Next page, I will write all these things. Lagging side, leading side. This E cos delta reactive power. Q is equal to V by XS. Okay. This earlier I have written. This is okay. These things is one set of. Now, main important thing is in the table from the graph, from the diagram, from the phasor diagram, it can be observed. It can be observed that. Lagging side and leading side. Let us make lagging side and leading side. What is your observation? Lagging power factor region. This is leading power factor region. And lagging power factor region. Lagging power factor region. Lagging power factor region. Leading side, lagging side. Lagging side. Now, I don't want to remember the diagram also. You can remember. See, this is V, na? See my hand. This is V. Okay, this is current. When current is lagging side, say, as load increases, E shift here, current coming closer. Current is coming closer. You can imagine in which direction phasors are rotating. Phasors are counterclockwise rotation. Na? As increases, delta also shift in counterclockwise direction. So when delta shift, when current is on this side, it will shift. It is coming closer to that. Closer to that means power factor is increasing. Load increases, power factor increases. Therefore, I can say power factor is proportional to mechanical power input and proportional to load. Proportional to load. Bigger one. This side also, I want to table size. Okay. proportional to mechanical power input. Let me write clearly. Power factor. Power factor is proportional to mechanical power input. That also proportional to load. But what about this side? Inversely proportional. Power factor is inversely proportional to mechanical power input and inversely proportional to load. And what about Q? Once you know the power factor, Q will be Q delivering, of course. Q delivering. That is inversely proportional to mechanical power input. Once the power factor decided, Q, don't think much. It is always inversely proportional to the power factor. Inversely proportional. Inversely proportional to the load. Remember that. Q inversely proportional to power factor always. And here Q absorption. Q absorption is proportional to mechanical power input and proportional to load. And what about IA? IA is always proportional to mechanical power input, proportional to load. Even leading side also, IA is proportional to mechanical power input, that is proportional to load. What about power? Delta. Delta also proportional both sides. Delta increases, na mechanical power input increases, delta increases. This side also, delta proportional to mechanical power input, proportional to load, delta. And active power also proportional to mechanical power input, proportional to load. And here also, power is proportional to mechanical power input and proportional to load. Right? These are the conclusions and the observations. Remember that these things. Now all the questions can be answered from these conclusions. You need not to by heart this. How phasor is shifting. That phasor must be in your mind. Okay. And for motor, it is going to be just quite opposite. Motor, E will be shift more lagging. Generator E more leading. Motor, it is going to be more lagging. Over now? Yeah. Now let us see some questions, objective questions. Okay. It's clear? Now let me give the questions. Okay. Yeah. So taken na? Fine. See. Question is an alternator operating in the bus bar. An alternator operating on the bus bar. Operating the bus bar at lagging power factor. Lagging power factor with constant mechanical power, with constant excitation. Constant excitation. Now, if the mechanical power input, increases, if the mechanical power input increases, then power factor dash, IA dash, delta dash, Q dash, P dash, E dash, V dash, F dash, N dash, TEM dash. Power factor, IA dash, delta dash, Q dash, P dash, E dash, V dash, F dash, N dash, TEM dash. Now, power factor. Power factor increases or decreases, lagging side. Now I can remember this is my voltage, this is current. When load increases, E will shift and IA also will shift. IA coming closer. And phi decreases. Power factor increases. Power factor increases. What about current? Current will be increases on both sides. Current increases, IA increases. Delta definitely increases on both sides. Q will decrease. Q delivering, observing. Q already delivering, lagging side means delivering, yes. But Q delivering, that will be decreases. And Q inversely proportional to power factor. What about P? P also increasing. We are increasing excitation, P increases. E also increases. No. E constant, no? E excitation is constant. So E constant. V also constant. V also constant. Now, question for you, E constant, V constant, then how IA increases? How IA increases? Delta increases. Vector difference. Though E magnitude, V magnitude constant, delta increasing, vector potential difference is increasing. That's the reason current increasing. F frequency always constant. N also always constant. What happened? Electromagnetic torque increase. That's the reason the power is constant. Here what we have done, our alternator, based on the alternator, when we are increasing mechanical power input, this is a prime mover, say, when you are increasing TPM also increases in opposite direction. This is omega, say, TM increases in opposite direction. As TPM increases, then TEM increases in opposite direction. TM increases in opposite direction. Therefore, omega constant. What is omega? Omega is equal to TPM minus TEM divided by B. So therefore, that is constant. Speed constant only. Then frequency also constant. Right? N constant, F also constant. Frequency also constant. The speed, frequency, voltage, all these are constant. Remember that alternate property in the bus bar, blindly you can say V, F, N. They are always constant. Okay? Yeah. Next question. See. Next question is, an alternator operating on the bus bar at leading power factor with constant prime mover input, constant excitation, not constant prime mover input, constant excitation. With constant excitation. Okay. Now, if the mechanical power input increases, or prime mover torque increases, meaning is same, prime mover torque also same. Prime mover torque increases. Mechanical power input, prime mover torque increases, or load increases, in other words. Load increases. Then what happened current? What happened power factor? Power factor dash, IA dash, delta dash, Q dash, P dash, E dash, V dash, F dash, N dash, TEM dash. What's your answer? Now machine is operating at leading side, left side. It is current is this side, leading side. And when load increases, what happened? E will be shifted like this. E will be shifted. When E shifted means current also going away from the voltage vector. It is going away from the voltage vector. When away from the voltage vector means phi increases, power factor decreases. So power factor will decreases. No? Yes, power factor decreases. IA definitely increases. Delta always increases. Both side proportional to load. Q will be absorbing, leading side not absorbing, but it is increase. Why? Because Q is inversely proportional to power factor. Inversely proportional to power factor. What about P? P increases. Five more input increases, P increases. E constant. V constant. F also constant. N also constant. TEM increases. TM will be increases. As TPM increases means TVM also increases. Then speed constant. In this, I am giving all varieties of questions. The examination, he can ask anyone. Either power factor he may ask, current he may ask, delta he may ask. For example, I will give one question, gate question. I'm not giving all the gate questions. I'm writing all the conclusions here. All questions I have added already. You can check it. You can find the answers. So for example, sample, let me give one question, previous gate examination. Gate 2008 examination question I will give. It's taken, yeah. See. So gate 2008 examination question for 2 marks he has given. Question is like this. An alternator operating on the bus bar. An alternator operating the bus bar, right, at UPF with constant excitation. If the load on the machine is reduced to half. The load on the machine is reduced to half. Then its operating power factor would be. Operating power factor would be A bit. Lagging B bit. Leading C bit. UPF D bit. Depends on the machine parameters. Depends on the machine parameters. This is a question. Depends on the machine parameters. Okay? Yeah. Then what is your answer? Alternator operating in the bus bar at UPF with constant excitation. If the load on the machine is reduced to half, then its operating power factor would be. What is your answer? Tell me, chat box. Lagging. B. Okay. So answer is lagging. Yes. Even if you draw the phasor diagram, you can observe na? Entire phasor diagram is not required. So this is V. You are at UPF. UPF means this is IA. You are at UPF na? For UPF means this is V. This is V. This is IA. V. This is E at UPF. But when this is delta, whereas when load increases, what is going to be happen? then E shift here, na? E will be shift here, E shift. So this is going to be E. Delta is reduced. This is E because delta reduced. Okay. Then this will be the IA into XS. This is IA into XS. When this is IA into XS means what is going to be happen? IA will come this side now. Yes. This is going to be IA. This is IA. Right? Yes. So for this E same. This will be lagging now. It will be lagging. Earlier it was UPF, but now it is lagging. Lagging. So answer is lagging. Not this much discussion. You see, phasor diagram. Current is here, UPF. But when load reduces, E shift here. Delta decreasing. Therefore, IA shifting. IA shifting. IA will come lagging side. If this load is increases, say it is going to be leading. Load increases, it will be leading, but lagging side. Fine? Yeah. See how simple question is. No paper, no pen is required. Directly you can able to see. Now, I will give one more question. Previous GATE examination question. See, some of the students are asking doubts. Sir, when class up to? Class will be up to, you told na, up to 8 or 8:30. I have received information 8:30, but what is the time? Just tell me. What is the timings according to you? Up to 8 or 8:30? 8, okay. Yeah. Yeah. Right. Fine. So 8 o'clock, 8:30. Okay, fine. I will continue up to 8 o'clock. Don't worry. And tomorrow is a holiday for you. Because tomorrow is a holiday. Tomorrow my class is not there. Okay. Tomorrow there will be no synchronous machine class. I don't know about other schedule, but so my class is not there. And the day after tomorrow I will continue. Okay. Today I will take up to 8 o'clock. This topic is almost completed. Just within 5 minutes we will complete this. We will shift to the synchronous motor. Last chapter, 7th chapter. And we will start the synchronous motor. After that we will go for break. Then we will continue up to 8 o'clock. In between we will take one break. Okay, na? Don't worry. Yeah. Now next question. See. Next question is. The question is like this. Previous GATE examination is also GATE examination question. An alternator is operating. An alternator is operating on bus bar. An alternator operating on bus bar. Alternator operating on bus bar at a load angle. At a load angle. At a load angle, delta is equal to 30 degrees. Delta 30 degrees with constant excitation. With constant excitation. With constant excitation. Constant excitation. Okay. Now, if the load on the machine is double, if the load on the machine is doubled, if the load on the machine is doubled, then its delta will be, then its load angle would be. Load angle would be, load is double. Load angle would be A bit. A bit 30 degrees, B bit 45 degrees, C bit 60 degrees, D bit 90 degrees. 90 degrees. 90 degrees. Okay. Tell me the answer for this. Right? Now, what is the answer? Initially, delta 30 degrees with constant excitation constant. But when load is doubled, then load angle would be 30 degrees, 60, 90, 45. Okay. So what is the answer you are expecting? Of course, some of the students may be expecting 60, not 60. Answer will be 90 degrees is correct. 90 is correct. 90. Why? Because see, power is proportional to, power is equal to EV by XS sin delta. But E constant, na? E constant, therefore power is proportional to only sin delta, because as EV all they are constant. Excitation constant, na? V, XS, E all they are constant. Therefore power is proportional to only sin delta. Therefore power P2 divided by P1C, P2 by P1. P2 is equal to E sin delta 2, not E also same. Sin delta 2 divided by sin delta 1. Sin delta 2 by sin delta 1. But P2 2 times of P1. P2 is equal to 2 times of P1. Right? Power double. Power load is double means power will be double. So 2 by 1 is equal to sin delta 2. Sin delta 1 is given. How much? Sin 30. Sin 30. Therefore, what is sin delta 2? Sin delta 2 is equal to 2 into sin 30. 2 into sin 30 means 2 into 0.5. That is equal to 1. Therefore, delta 2 is equal to 90 degrees. That would be your answer. 90 degrees. Okay? It means when load is doubled means don't think delta is not going to be double. No. Delta is not double. Right? Okay. Yeah. Right? Just a minute. Okay. Yeah. Right. Right. Okay. Let us do. It is also, I think it is better to do the problems simultaneously on this topic. We have completed this topic now, so it would be better. Let us do the problem. Yeah. Okay. See, dear students, take down this problem because ultimately gate examination means problems, no? Problems. It will be better doing the problems on this. Okay, before that, some of the students are raising your doubts. Okay, tell me what is your doubt? Some of you have raised your hands. What is your doubt? Hello? 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 Okay. So if you do the problems, whatever the conclusions we have done, all the observations we can make it, right? So let us do the problems based on this. I will do on one concept, one problem. That will be enough. Yeah. So take down this problem. Problem is on page number 49 to 52. 49, 50, 51 and 52. 52. Problem is a three-phase turbo alternator. A three-phase turbo alternator with a synchronous reactance of 10 ohms. 10 ohms per phase. 10 ohms per phase and negligible armature resistance. Negligible armature resistance. Because problems are important. Na? If you neglect problems, we are neglecting our gate examination. So better to do the problems now itself. After this, we will go for synchronous motor. Negligible armature resistance is connected to 11 kV constant voltage and constant frequency bus bar. Constant voltage, constant frequency means it is infinite bus bar. Constant voltage and constant frequency bus bar. And supplies 100 amperes. 100 amperes at UPF. Supplies 100 amperes at UPF to the system. If the turbine power is kept constant, is kept constant and the excitation of alternator is increased by 25%. Okay. Then the new load angle would be in question number 49. The new load angle would be okay. No load angle would be ABT 8 point. I don't want to write the options. Options you can see in the booklet. No load angle would be 50. Question number 50. The new current would be the new current is dash amperes. 51. New power factor. The new power factor is dash. So question is only up to 51, not 52, 51. So very, very important question. But a conceptual based question. Okay. Question is clear, I think. What is the question in that given alternator? Synchronous reactance is given 10 ohms per phase. RA neglected. Is connected to 11 kV bus bar, 11 kV line voltage bus bar. Constant voltage, constant frequency, and infinite bus bar. And supplies 100 amperes at UPF. It is supplying 100 amperes at UPF. If the turbine power is kept constant, mechanical power input is kept constant. Excitation is increased. Excitation of alternator increased by 25%. Okay, this is the first topic. The question is related to Vickers and inverted Vickers. V and inverted Vickers. Right? Excitation increased 25%. What is going to be happen? Can you tell me answer? Is it lagging power factor Earlier, now it is operating at UPF, na? Dear students, is operating at UPF. When excitation increases, what is going to happen? Power factor? Power factor will becomes lagging power factor. Current is 100 amperes. Current is 100 amperes. What is going to happen? Current, tell me. Can you expect the answer? Current will be, you are at lagging side. UPF. Current is going to be increase. Power factor will reduce. Lagging side power factor. V curves, inverted V curves. Delta also. Right now 100 amperes UPF, some delta is there. When excitation increases, delta will reduce. All conclusions, I will also correlate at the end. First, let us do the problem. Yeah. See. Solution. First, what is the data given? An alternator supplying a three-phase alternator. What is voltage? Line voltage 400 kilowatts. Right? Three-phase alternator, turbo alternator. Its reactance is given. Excess is how much? 10 ohms per phase. 10 ohms per phase. But line voltage is how much? Line voltage is 11 kV. Line voltage is 11 kV. Then what is V phase? V phase is equal to 11 into 10 power 3 divided by root 3. That is 6350. 6350.8 volts. Or roughly it is 6351 volts. 60585 volts. V line. V phase is equal to that much. And operating at what frequency? Operating at supplying. It is supplying 100 amperes. Supplying 100 amperes at UPF. Supply 100 amperes at UPF. Mechanical power input is constant. P mechanical is constant. But excitation is increased. Excitation is increased by 25%. 25% means what is that? E dash is equal to 1.25 into E. 1.25 into E. Then what is the E is asking? Then what is the new current? Then what happened current? Then what about delta? Then what happened delta? What happened current? What about the power factor? These are the things. Okay. Yeah. So first you have to calculate E value. E. That E is equal to at 100 amperes. That IA is equal to 100 amperes, comma UPF. Calculate E value. Calculate E value. E is equal to. That E is equal to how much? E is equal to V plus IA ZS. V plus IA ZS. V0. Its magnitude will be V plus IA ZS. But not just a arithmetic sum. It will be V0 plus IA plus or minus 5 into ZS at an angle theta. ZS at an angle theta. Or else you can also use the equation V cos phi plus IA RA whole square plus V sin phi plus or minus IA x's whole square. Also you can use. You will get the same value. Okay. But it is not just arithmetic sum, dear students. It's not just arithmetic sum. It will be vector sum. Vector. So calculate E value. E is equal to. That E is equal to V0. V is phase values you have to substitute. 6350.85 at an angle 0 plus IA is equal to how much? 100. 100 at an angle 0. UPF na UPF. Unity power factor 50. Angle. ZS how much? 10. 10 at an angle 90 degrees. So what is your E value? E value. That E is equal to 6429. 6429 at an angle 8.94 degrees. That is a delta. Right now delta. The delta is related to what? 100 amperes and UPF. At 100 amperes and UPF. But when excitation is increased, excitation increase, delta is going to be decrease. When excitation is increases, say, delta will reduce. That we need to find. So when excitation is increases, see, mechanical power input constant, but excitation increases, delta will change. Since excitation is constant, sorry, since mechanical power input is kept to constant, mechanical power input is kept to constant, therefore P constant, P constant means that is P constant. But whereas excitation is increased, na? Excitation is increased. First let me write, excitation is increased. Excitation is increased. As excitation is increased by 25%. That is E dash is equal to 1.25 into E. 1.25 times of E. 1.25 times means 1.25 into E how much? Yeah. E is equal to 6350. 6350 volts. 6350.85 volts. Correct? E. No. E is equal to 6429. No? Sorry. E is equal to 6429. E is equal to 6429. Yeah. But since mechanical power input is constant, since mechanical power input is kept to constant, mechanical power input kept constant, therefore P is constant. P constant. P means P dash is equal to P, say. P dash is equal to P. That is nothing but E dash sine delta. E dash V by XES sine delta dash is equal to EV by XES sine delta. Sine delta. But V everything is constant, na? Therefore, E dash sine delta dash. Delta will change. When excitation change, delta changes. Is equal to E sine delta. E sine delta. This already we know. E1 sine delta 1 is equal to E2 sine delta 2, na? Yes. I am taking delta dash. New values delta dash. E dash is equal to, yeah, E dash is equal to 1.25 into 6429 sine delta dash is equal to how much? E. E is equal to old value. E is equal to 6429. 6429. Okay, into sine delta. What is the delta sine delta? 8.94. No? 8.94 degrees. Therefore, what is E dash? Delta dash. Then delta dash is only unknown. Delta dash is equal to how much? 7.14 degrees. 7.14. That will be the answer. Delta. The excitation 25% increases. What will happen? Delta has reduced. Earlier it was 8.94. Na? At 100 amperes UPF 8.94. It has reduced. Similarly, next question. What is another question? Yeah. There is a 49 question. 49 question, new load angle. Question number 49. Oh. Now 50, question number 50, new current. New current is equal to IA dash, say. What is IA dash? IA dash is equal to E dash delta dash minus V0 divided by ZS at an angle theta. The delta also changes, na? Yes. E value, new value, how to substitute? What is E dash? E dash is equal to 1.25. 1.25 into E is equal to 6429 delta dash. Delta dash how much? 7.14 degrees. Minus V. Minus V is equal to 6350.85. It will be 0. V will be 0 E delta by ZS. ZS how much? 10 at an angle 90 degrees. What is this current? IA dash. IA dash is equal to, you will get 190.6 amperes at an angle minus 58.39. Minus 58. That is itself a 5. Minus 58.39. So current is 190.6. Then 51, new power factor. This is new current, new IA. New power factor is equal to cos phi. Phi dash say, cos phi dash. That is equal to cos 58.39. Is equal to how much? 0.524. Lagging or leading? It is lagging. Lagging. Okay, it is lagging. Lagging. Therefore, we have observed all the conclusions. No? We have observed all the conclusions. See, if you draw the conclusions here, power factor has reduced, delta has reduced. Okay. And current is increased in 100 amperes. Current is 196. So this question is related to Vickers and inverted Vickers. In this, what is our observation is, yeah. Delta, IA and power factor. So this is IA, is the power factor. This is leading side, lagging side. Initially, where your machine is here, operating here. Okay, UPF, power factor UPF it was. And what is the current? Current is 100 amperes. Current is 100 amperes. Current is 100 amperes. 100 amperes current. What is the delta? 8.94 initially. 8.94. Okay. Yes. Now, when excitation is increases 25%. See, when excitation increases means we are here. When excitation is increased, we are here. What happened? Power factor has reduced. Power factor is equal to how much? 0.524 lagging. 0.524 lagging. It has reduced. Then what about current? Current has increased. Current, new value. How much it is? 190.6 amperes. 6 amperes. What about the delta? Delta has reduced. Delta has reduced to 7.14. 7.14. Okay. All that has changed or not? Yes. That changed. So whatever we have discussed with numerical values, you will get the same thing. Numericals also you will get the same thing. Okay. Fine. Yeah. Right. Anyhow, we are going to do some other problems at the end, total after completion of this topic, same as generator and motor. Same problem also you can do as a generator, as a motor also you can do is. You can do the same problem. Vickers, inverted Vickers are same for generator and also motor. Only difference is equations are different. Okay. So after completion of synchronous motor, again we are going to the problems. But now just let me start with the synchronous motors. Okay, synchronous motors. Yeah, see. Yes. Some of the students, your doubt is P mechanical changing. What is the meaning? P mechanical changes means mechanical power input changes. When P mechanical changes means P electrical changes. P electrical increases means it is taking more load. All meanings are same. Mechanical power input increases means electrical power increases. Automatically prime mover torque increases. Load also increases. All meanings are same. So 4 examiners are there. They will use 4 types of questions. Okay. Yeah. Problem, huh? You want to see, some of the students are asking, show the problem once. You can take the screenshot. This is a problem. Okay. Now, then just let us start with our synchronous motor and we will go for a break in between. Yeah. Okay. So our next topic is synchronous motors. Synchronous motors. Synchronous motors is a chapter number 7, last chapter. Synchronous motor. Coming to synchronous motors, to most of the application point of view, what are the motors? Most of the application point of view are the induction motors are best. Nearly 80% of the motors application point of view are the induction motors. It may be domestic application, commercial, any applications you take, industrial applications, mostly induction motors. Why? Because induction motors, the advantage of induction motors, they are rugged in construction, easy of speed control, speed can be easily controlled, right? And less cost, less maintenance, almost less maintenance, speed control is easy. Particularly squirrel cage induction motor, maintenance less maintenance, and cheaper also compared with all other motors. When compared with DC motor, synchronous motor, induction motor is cheaper. Induction motor is cheaper. That's the reason induction motors are widely used. But where synchronous motors are preferred for large power, low speed applications. For large power, low speed applications, synchronous motors are preferred. We are going to see why. For example, induction motors can be used for all ranges. If like for 100 megawatt motor at 1000 RPM, I will prefer induction motor is preferred. Sorry, 100 megawatt, right? 100 megawatt, 300 RPM say. 300 RPM means then we will mean the synchronous motor is preferred. A large power, low speeds, synchronous motors are preferred. Induction motors will be preferred for everything. When comparison is large power, low speed. But induction motor will have all ranges. Few watts to hundreds of kilowatts, megawatts also. But when comparison large power, low speeds, synchronous motors are preferred. Why? Because synchronous motors are cheaper. For large power, low speed applications, synchronous motors are cheaper and they are small in size compared with induction motor. Only for large power, low speed applications. That's the reason most of the synchronous motors are salient type. Salient pole motors are preferred. Because it is preferred for low speed. Based on the rotor construction, there are two types of synchronous motors. There is no difference between construction of alternator and synchronous motor, no construction difference. Same machine can be used as a generator and motor. Just like DC generator can be used as a DC motor, induction motor can be used as induction generator. Similarly, synchronous motor also can be used as synchronous generator. Generator also can be used as motor. So constructionally, there is no difference. Both are same. Right? So there are two types of synchronous motors. Salient pole synchronous motor, cylindrical rotor synchronous motor. Right? But most of the synchronous motors are salient type. I'm going to write first listen. Salient pole motors are preferred. Why? Because in salient pole motors, advantage of salient pole motor is more stable and more power output in salient pole. Why? Why? Because extra reluctance power. You remember, reluctance power is extra. And extra reluctance power means, do you remember, v square by 2 1 by x cube minus 1 by xd, 15 to 20% power extra. Even if you design, you can go up to 30% also. So power output is more, stability is more. That's the reason salient pole motors are preferred. Correct? The generator, in generating stations, there is not our choice. Generating stations, if it is steam power stations, means you have to go for cylindrical only. Hydro power station, you have to go for salient. There is no our choice, compulsory turbine choice. Based on the generating station, you have to choose. But motor, we can choose any motor. Any motor, I can choose induction motor or synchronous motor. But when synchronous motor means, I will give the preference for the salient pole motor because it is small in size and more power output, more stable. That's the reason most of the synchronous motors are salient. See here, most of the motors are application point of view. Most of the motors application point of view. Most of the motors application point of view are the induction motors. Or the induction motors. Nearly 80%. Nearly 80% motors. Because induction motors are rugged in construction, okay, and easy of speed control. Speed control is easy of speed control, small size, compact size, less maintenance, and less cost, cheaper. Compared with all other motors, cheaper. Right? Due to these advantages, induction motors are popular. But at the same time, synchronous motor also competitive with induction motor. But they are preferred for large power. Synchronous motors are preferred. Synchronous motors are preferred for large power, low speed applications. Because at large power, low speeds, synchronous motors are cheaper. And small in size. Compared with equivalent rating of induction motor. Equivalent rating of induction motor. Okay, that's the reason it is preferred. And constructionally, there is no difference between synchronous motor and synchronous generator. Constructionally, there is no difference between synchronous motor, alternator, and synchronous motor. No difference. Same machine can be used as a generator and motor. Therefore, based on the rotor construction, Based on the rotor construction, two types of synchronous motors. Based on the rotor construction, two types of synchronous motors. Two types. What are they? Number one, salient pole synchronous motor. Salient pole synchronous motor. And second one is cylindrical rotor synchronous motor. Both same. Cylindrical construction already we have seen a cylindrical rotor synchronous motor. But most of the synchronous motors are salient type. Most of the synchronous motors are salient type. Most of the synchronous motors are salient type because preferred for low speed applications. Synchronous motors, salient pole motors only low speed applications. Na? It's preferred for low speed applications. And also salient pole motor is more stable. Salient pole synchronous motor is more stable and more power output. More power output due to extra reluctance power. Okay. Due to extra reluctance power, salient pole machine is more stable and more power output. That's the reason they are preferred. Okay. Now. Yeah. Synchronous motor will always rotate only at synchronous speed. Na? Yes. Synchronous motor. It is always connected on the bus bar. Yes. Given with excitation. Okay. So, see, based on the current, this is North Pole and South Pole. When machine is connected to the bus bar, it will draw the current. And then poles will form. Na? Yes, stator poles will form. South Pole and North Pole. Stator poles will form. They rotate at synchronous speed. These poles will rotate at synchronous speed, say 3000 RPM. 3000 RPM. Synchronous speed they will rotate. When they rotate at synchronous speed means rotor also will rotate at 3000 RPM only. Synchronous speed. Why? Because due to magnetic locking between stator poles and rotor poles. Due to magnetic locking between stator poles and rotor poles, both will rotate with the same speed. Stator poles and rotor poles. Magnetic locking. So synchronous motor will always rotate only at synchronous speed. Due to stator poles as rotate and rotor also will rotate at synchronous speed. When the supply is given, RMF is produced, then rotor also will rotate at synchronous speed. Of course, it is not self-starting that we are going to see. I am discussing under running condition. So synchronous motor is called constant speed motor. It is always rotate only at NS. Synchronous motor, when supply is given to the synchronous motor, when supply is given to the synchronous motor, stator poles are formed, and rotated synchronous speeds. Rotated synchronous speed. Rotated synchronous speed. Then rotor also rotate. At synchronous speed. Due to magnetic locking between stator poles and rotor poles. Stator poles and rotor poles. So rotor rotate only at synchronous speed. Synchronous motor is called doubly excited machine. Synchronous motor is called doubly excited motor. Doubly excited means armature is excited with AC, field is excited with DC. Armature is excited with AC, but field excited with DC. Okay, doubly excitation. So due to this doubly excitation, rotor rotate only at synchronous speed due to magnetic locking. So due to this doubly excitation, rotor rotate only at synchronous speed. Okay. Doubly excited means magnetic locking. So synchronous motor is a constant speed motor. Synchronous motor is a constant speed motor. Synchronous motor is a constant speed motor. The constant speed motor. It always rotate only at synchronous speed. Rotated synchronous speed. Only at synchronous speed. Only at ns. But what is that ns? Ns is equal to 120 into F by P. Rotate only at synchronous speed means ns 120 into F by P mean, right? Yes. Now how can you control speed of synchronous motor? It rotates only at synchronous speed. Speed can be controlled only by changing the frequency. Rotate only at synchronous speed. Taken up to here? Yes. Next. When F changes, what will happen? Ns changes. When F changes, RMF speed only changes. It will draw the current, and when frequency changes, rotating magnetic field speed changes. Then rotor also will rotate with the same speed. So south pole, when frequency changes, stator poles rotate fastly, then rotor also rotate fastly. They will take away. With magnetic locking, they will pull the rotor, rotated synchronous speed. So it will rotate at ns, say. Ns is equal to 120 into F by P, say. 120 into F by P. If you change the frequency, then ns changes. If the speed can be controlled, the speed of synchronous motor can be controlled only by changing the frequency. Yeah, the speed can be controlled. The speed of synchronous motor can be controlled. Synchronous motor can be controlled. By changing the supply frequency. When When supply frequency changes, NS changes. Okay, that is when frequency changes. When supply frequency changes, what will happen? NS changes. Supply frequency changes, stator fold speed, stator pole's speed changes. That is NS changes. NS changes. Thereby rotor speed changes. Thereby rotor speed changes. Rotor speed changes. For example, a four-pole synchronous motor, say. For example, a four-pole synchronous motor, if frequency, if F is equal to 50 hertz, say, F is equal to 50 hertz, what is NS? NS is equal to 1500 RPM. NS is equal to 1500 RPM. If frequency is equal to 30 hertz, say, 30 hertz, what is NS? NS is equal to 750 RPM. 750 RPM. Not 750, 900, 900. 900 RPM. If frequency 25 hertz, say, 25 hertz means then NS is equal to 750 RPM. NS is itself changes. Dear students, NF itself changes. NS changes and frequency changes. But as long as, if you draw the characteristics here, speed torque characteristics, this is the speed. If you take this is load or IA. This is load or IA. Speed remains constant as long as frequency constant. If you take here, this is for what? This is as long as your frequency 50 hertz, say, there is a synchronous speed is 1500 RPM. It rotated 1500 RPM only. When frequency 50 hertz. Speed constant as long as your frequency 50 hertz, say, it may be no load or full load, whatever it may be, its speed is remains 1500 RPM, 1500. Okay. And if it is 30 hertz, say, if it is 30 hertz means your frequency is 30 hertz, what is its speed? Its speed will be 900 RPM only. It will rotate only at 900 RPM. This is itself NS. This is itself NS. It will rotate only at 900 RPM. And as long as your frequency is 25 hertz, it will rotate only at 750 RPM. 750 RPM. Why I am drawing this diagram? Students will raise a doubt. Sir, you told synchronous motor is constant speed, but it is changing. How can you control the speed? At what speed it is rotating, that only synchronous speed. Dear students, synchronous motor, it rotating 900 RPM, 900 RPM only synchronous speed. For which frequency? 30 hertz. As F changes, NS itself changes. NS changes. So it will continue to rotate only at the same speed. The constant speed means it is independent of load. Load changes also, speed will not change. As long as your frequency 30 hertz, say, its speed remains 900 RPM only. Okay, that is the meaning of it. Constant speed machine means that is the meaning of it. Okay. So as NS changes, as frequency changes, NS is itself changes. Okay. Therefore, rotor speed also changes. Then rotor speed also changes. Right? So speed can be controlled by changing the supply frequency. How you can change the supply frequency? By using any frequency converter. If you connect a cyclo converter, frequency can be changed in a frequency converter. Supply frequency 50, say, before giving to the motor, you need to change the frequency. but speed cannot be controlled by changing the pole. Changing is not possible. Pole changing is not possible. Practically, pole changing is not possible. Practically, pole changing is not possible. Pole changing method. Pole changing is not possible. Pole changing is not possible. Now the induction motor, I think you might have seen that. For induction motor, pole changing is also possible. Because when stator poles are changed, rotor poles, their poles are induced poles. Correct? Their poles are induced poles. When stator pole changes, rotor poles automatically changes, induced poles. But here, in our synchronous machine, is it induced poles? No. These are fixed. So for example, salient pole rotor, 2-pole rotor is there. 2-pole rotor. Can you convert that into 4-pole rotor? You cannot convert. Stator poles can be changed. And the stator, if it is 3-phase machine is there, na? Just like a induction motor, stator poles you can change by changing the connection. Connections, whatever existing winding you can change so that stator poles can be formed. It can change. But rotor poles can you change? If it is 2-pole rotor is there, 2-pole salient pole rotor is there. If you want to change the poles means you have to remove that rotor. Remove that rotor and you keep another 4-pole rotor. Is it called speed control? No. Whatever existing rotor you can change means pole changing is not possible in synchronous motor. Induction motor is possible. Okay. Yeah. Now, again, can you change the speed of synchronous motor by changing the supply voltage? No. Speed cannot be controlled. Induction motor speed can be controlled by changing supply voltage, but here not possible. Speed of synchronous motor cannot be changed. Speed of synchronous motor. I am giving all the statements directly. Speed of synchronous motor cannot be changed. Cannot be changed by changing the supply voltage. By changing the supply voltage. No, supply voltage. Speed is independent of supply voltage. It does not depend on the supply voltage. Okay, this depends upon only frequency. Induction motor side, rotor side control is possible. Induction motor. But is there any rotor side control is possible? No. Rotor side speed control is not possible in synchronous motor. Rotor side speed control. Rotor side speed control is not possible. Not possible in synchronous motor. Not possible. But slip ring induction motor it is possible. Na? Slip ring induction motor by adding external resistance, etc. Possible. But here it is not possible. Rotor side speed control is not possible. Only stator side, that will be supply frequency only. If you change the field current, will be there any change in its speed? If I change the field current, will be there any speed control? No. DC motor speed control is possible. By changing the excitation, speed can be controlled. But synchronous motor, speed does not depend on the excitation. Speed cannot be controlled. Speed cannot be controlled. Cannot be controlled by changing the field excitation. By changing the field current. No. By changing the field current, speed you cannot change. The speed can be changed only by changing the stator field speed. If you change the stator field speed, then only rotor speed will changes. There is no other way. Ultimately, you have to change the stator poles. At what speed stator poles rotate, rotor poles. How you can change the stator poles? By changing the frequency. By changing the frequency. Therefore, speed only can be controlled. Speed can be controlled. Speed is only controlled. Only controlled by changing the speed of stator poles by changing the speed of stator poles. Change the stator poles speed. Okay, that can be done by stator pole speed. Changing the speed is only controlled by changing the speed of stator poles speed, so that rotor poles also rotate with the same speed. So that rotor poles are rotor poles. Rotor poles will rotate. Rotor rotate at synchronous speed. Rotor rotate at same speed. That is called what? That is itself synchronous speed. That is itself ns. Okay. It does not depend on the field current. So therefore, speed can be controlled only by supply frequency. Speed can be controlled only by changing the supply phase sequence. Okay, supply phase sequence. Yeah. And if you draw the speed versus torque characteristics, how synchronous motor, speed versus torque, say. For example, this is speed and torque. How the characteristics? Constant. Speed constant, always constant. Speed remains constant. Torque changes or current changes, whatever it may be. Whatever may be the x-axis, y-axis speed constant. In your examination, the question was, he has changed the axis. He has given speed here and torque here. How it will be, tell me? How it will be? It will be like this. Both are same. Speed, torque, and when you change the x-axis and y-axis. This is the torque and this is the speed. How they will be? Like this. Torque versus n, same. Similarly, if you draw the speed versus frequency, how it will be? If you draw speed versus n, how it is? N versus frequency. N versus frequency means it will be linear. Okay. Why? Because ns is equal to 120 into f by p. Therefore, ns is proportional to frequency. Therefore, n versus f is linear. Characters are linear. Speed versus frequency, it will be linear. Okay. Yeah. Linear. And then how the direction of rotation of synchronous motor can be reversed? Direction of rotation of synchronous motor can be reversed only by changing the supply phase sequence. Direction of rotation can be reversed only by changing supply phase sequence. Direction of rotation does not depend on the direction of the field current. Let us see. The direction of rotation of synchronous motor can be reversed. By changing the supply phase sequence. Direction of rotation does not depend on direction of field current. Okay. It does not depend on direction of field current. So it is depends upon only supply phase sequence. Let me show how it is. It does not depend on direction of field current. In DC motor, how you can change? If you change the direction of field current, and there direction of rotation will changes. Direction of rotation will changes. But here no, not possible. See, when phase sequence changes, what is going to be happen? These are poles say. North pole and south pole, north and south pole. When excitation is given, this is south pole and this is north pole, north pole. For phase sequence, in which direction RMF will rotate? For RYB phase sequence, say, they will rotate in clockwise direction. Rotate for RYB. For RYB phase sequence, this RYB phase sequence, say. For RYB phase sequence, RMF will rotate in clockwise. For RYB phase sequence, see, RMF rotate in clockwise. RMF means stator poles. Stator poles rotate clockwise. Then rotor also will rotate in clockwise direction. So clockwise direction. Rotation is clockwise. Rotor rotate clockwise. Rotor rotate clockwise direction. Clockwise direction. But if you change phase sequence, what will happen? If you change phase sequence, rotor will rotate opposite direction. In this is the phase sequence, say. You are changing RBY. RBY means then RMF rotate in which direction? This RMF rotate in counterclockwise direction. Yes. For RMF itself rotate in counterclockwise direction. RMF. When RMF counterclockwise direction means rotor rotate. Rotor rotate in counterclockwise direction. Rotor rotate in counterclockwise direction. Rotor also will rotate in this direction. Okay, rotor also will rotate in this direction. Red color side, counterclockwise direction. If you change phase sequence, rotor rotation automatically it will changes. Clockwise or counterclockwise. Fine. But it does not depend on the field current. I am taking field current here same. Field current same, but if phase sequence changes, definitely rotor rotation changes. Because these poles will rotate in this direction, red color, poles rotate in this direction, then automatically rotor also will rotate. In which direction stator poles rotate? Rotor rotate in the same direction. Rotor rotate in the same direction. Now, if let me change the field current, what is going to happen? Just observe, if field current changes, if you change the field current, field current changes, why speed is not changing? Let us observe that. Phase sequence I am keeping same. See, for this given field current, plus minus, this is north pole, this is south pole, north and south pole. Okay. And here it is stator pole, south pole and north pole, say stator pole, south pole, north pole. Then the south pole rotate in clockwise direction. The north pole also will rotate in clockwise direction. Due to magnetic locking, both will rotate in same direction. Both will rotate in same direction. Same direction. For the given field current direction in this is IF. This is IF. But when field current changes, when field current changes, what will happen? See, I am changing the field current here. Here it is rotating, rotor is rotating in clockwise direction. It is rotating in clockwise. Now, I am changing the field current, you see. When field current, this is minus and plus. Field current has reverse. Direction of field current has reverse. IF. IF is reversed. The polarities we have reversed. But first instant, south pole I am taking, same instant let us take. Same instant if you take, this is becomes south pole and this becomes north pole. Correct? When field current is reverse means polarities will change. South pole, north pole. South pole, north pole. Okay? Yeah. But the stator poles, as long as phase sequence same, phase sequence is RYB only. Here also I am taking phase sequence same, RYB only. I am not talking about the phase sequence. Phase sequence same. Then stator poles rotate in the same direction. Stator poles rotate in the same direction. Stator poles rotate. Now what the south pole will do? At that instant, south pole is repelling. South pole repel. When south pole repel means, of course, the rotor may repel, south pole may repel, rotor may come to here. Just imagine rotor may come to here. Rotor is coming to here. The south pole. This is repelling, na? Repelling. So south pole will come to here. North pole is coming to here. Then rotor will continue to rotate. Just a minute. See, listen first. Stop writing. Rotor will repel it is, and it will rotate in counterclockwise direction. Huh? Will it continue to rotate counterclockwise direction? No, no. At that instant, south pole is repelling the south pole. But later onwards, nobody is there. South pole is rotating in clockwise direction. Just to repel at that instant, okay. Later onwards, south pole is moving in this direction. No one is there to repel continuously. Then what this north pole will do? North pole will wait for the south pole. South pole is rotating now. South pole is coming to here. South pole is coming to here. South pole came to here. South pole came. Now these two are magnetically locked. Magnetically locked. Then rotor will rotate like this. Rotor will rotate. Similarly, this north pole is coming this side, na? Yes. North pole is coming to here. North pole is coming to here. North pole came to here. Both are magnetically locked. Now both are magnetically locked. Okay. Then rotor rotating clockwise direction only. Clockwise direction only. So rotor rotation clockwise. Here rotor rotation clockwise. Here also rotor rotation clockwise. Rotor rotation clockwise. Here also rotor rotation clockwise only. Okay. Even if you change the field current, what is going to be happen? The poles are changing, rotor poles are changing. But that one particular instant, not at that instant. Within one rotation, definitely the north pole is magnetically locked with south pole. Therefore, in which direction stator poles are rotating, rotor poles rotate in the same direction. So ultimately, I can write only one statement. Direction of rotation is depends on the stator poles only. In which direction stator poles rotate, rotor rotates same. And here what we are doing, as long as phase sequence is same, say stator poles rotation same. When stator poles rotation same means rotor rotation also same, irrespective of field current. Right? Yes. Ultimately, the rotor always rotate. The rotor always rotate in the direction of stator poles. The direction of stator poles rotation. The direction of stator poles rotation, irrespective of field current. Irrespective of direction of field current. Direction of field current. Okay. When field current changes, polarities are changes. But one particular instant, opposite poles are magnetically locked. So ultimately, stator poles are rotating clockwise. So rotor also will rotate in the same direction. Okay. Yes. Now, then coming to applications of synchronous motor. Applications. Okay. Yeah. Applications of synchronous motor. Synchronous motor, it can be used for large power low head pumps. Yes, we'll go for a break just after 5 minutes. 5 or 2 minutes it is going to become. For large power low head pumps. For large power low head pumps. And large power low head pumps. And also reciprocating pumps. Reciprocating pumps. Low head pumps. Yeah. Reciprocating pumps. Centrifugal pumps are there. Generally, you will use centrifugal pumps. Pumping of water. Reciprocating pumps also. Reciprocating means they will move up and down. Okay. Pumping. But motor rotate clockwise. One particular direction. Motor rotation circulation. But pump will move linear motion. It is translation. Rotation can be converted into translation. And water will be upwards. Pumping of water. Reciprocating pumps. Steel mills and rolling mills. Steel mills and rolling mills. Rolling mills. Induced and draught fans. Induced and draught fans. That is exhaust fans. Exhaust fans. Exhaust fans. The exhaust fans speed is constant or varying? Constant. Fifth one, crushers and blowers. Crushers and blowers. Blowers. Synchronous condenser. Synchronous condenser. Synchronous condenser. Now for power factor correction, synchronous condenser is nothing but for power factor correction. Okay, yes. In all applications, all these are constant speed applications, constant speed. Can you tell me pumping of water, is it constant speed or variable speed drive? Constant speed. When your house pump is there now, water pumping, you are pumping water from ground floor to 10th floor. Are you controlling any speed? No. If you increase the speed, will it pump more water? No. Water is there, water will come. If there is no water, what is the use of it increasing speed? Generally, it can be operated constant speed. Reciprocating pumps. All these are synchronous motors are used generally constant speed motors. Yes. Induced fans. Exhaust fans are constant speed. You cannot control speed, not necessary. Exhaust speed is constant. In your house, exhaust fans are there. Is there any speed control? Not necessary. Synchronous condenser. These are the applications of synchronous motors. And what are the advantages of synchronous motor? Advantages. Let us see. Advantages of synchronous motor. Advantage. Advantages of synchronous motor. The advantages are, number one, it can be used for large power, low speed applications. Synchronous motors are cheaper. I have given a very beginning. Large power, low speed, synchronous motors are best. For large power, low speed application, for large power, low speed applications, synchronous motors are preferred. Synchronous motors are cheaper and small in size. Cheaper and small in size compared with induction motor. Large power, low speed applications. And similarly, second one is power factor can be controlled. Power factor can be controlled. Constant speed also an advantage. Constant speed. Speed is extremely constant. Constant speed. Right? Constant speed. Okay. What is the slip of synchronous motor? Constant speed. Slip of synchronous motor is slip of synchronous motor. Let me add in the beginning slip speed regulation 0 ne. Slip of synchronous motor. Let me add here itself. Slip of synchronous motor. Slip of synchronous motor. Yes, what is S? S is equal to Ns minus Nr by Ns. So that is Nr, Ns. Nr is equal to Ns by Ns. What is that? Slip is 0. Synchronous motor slip is 0. 0 slip motor. Slip 0. And what is speed regulation? Speed regulation is equal to no load speed minus full load speed by full load speed into 100. Here, no load speed also Ns, full load speed also Ns into 100. What is that? 0%. Speed regulation is 0. Slip of synchronous motor also 0. It's an extremely constant speed motor, no? Yes, extremely constant speed motor. Speed is 0%. Speed regulation is 0. No drop of speed. You can also see the characteristics here, no? Yes. Yeah. So, constant speed motor. Speed is extremely constant. And third one is power factor can be controlled. Power factor can be controlled. No motor it is possible. Power factor can be controlled. Okay. It can be operated better power factor. Therefore, efficiency, good efficiency. Good efficiency because can be operated at good power factor, can be operated better power factor. Therefore, better efficiency. Efficiency is better. Compared with induction motor, synchronous motor efficiency is more. Good efficiency. All these are advantages. But what are the disadvantages? Tell me. Disadvantages. These are the advantages. No? But disadvantages are it requires DC excitation. Requires DC excitation for field. DC excitation for field. DC excitation is required. Second one, stability problem. Synchronous motor, it rotates only at synchronous speed. Na? Stability problems. It experiences stability problems. And other disadvantage is synchronous motor is not a self-starting motor. Synchronous motor is not a self-starting motor. Not a self-starting motor. Right? Yes. Starting torque is 0. Starting torque of synchronous motor is 0. Starting torque is 0. But develop running torque. But develop good running torque. Develop good running torque. Problem is with starting. Running torque. Okay. Running torque. The synchronous motor starting torque divided by full load torque is equal to how much? 0. Starting torque by full load torque 0. But what is full load torque divided by starting torque? That is equal to infinite. Just to have idea about these things. Starting torque by full load torque 0. Full load torque by starting torque is infinite. So some examination questions that is. Okay, starting torque is 0. So then after the break, we are going to see why synchronous motor is not self-starting. Synchronous motor is not self-starting. Why? Why synchronous motor? Synchronous motor is not, that is the main drawback. Synchronous motor is not self-starting. Self-starting. Okay. Why it is not self-starting? See after the break. We'll see after the break. So break for 20 minutes. Then class will start. Anyhow, don't worry. I will try to close at 8 o'clock. 8 o'clock we will close. Class will start at 7. Okay, or let us take one thing. Better do 15 minutes. 15 minutes break, and then class will start at 7:02. Okay, na? Yes. Okay, take the break and then come back. Yeah. Some students at what motor that is used to lift the water pump, induction motor. That will be induction motors for large power pumping of water, like a hydroelectric power station. See, some of the students is asking a doubt, sir, which motor can be used in water pumping in house? Houses you can use induction motor only, but very large size means, for example, you take pumped storage plants are there, na pumped storage plants. Hydro power station, it will be pumped storage plants. For pumped storage plants, same machine can be used as a generator and also motor. When water is coming from reservoir to generator heating, and after that water is released into the tail race, that act as a generator. Salient pole machine. Salient pole machine, pumped storage plants. I think you know pumped storage plants. When water is coming from reservoir to tail race, the water hit the turbine, and after hitting that, water is released into the tail race. It acts as a generator. But now if you want to pump the water from tail race to reservoir, then it acts as a motor for pumping of water. Same turbine, reversible turbine will be there. Reversible turbine, it will pump the water. So such type of pumping of water, synchronous motors are used. Now you can see how large amount of water to fill the reservoir, to pump the water from reservoir means very large. It's not just for our domestic applications. Okay, and such type of large bulk amount of water pumping, synchronous motors can be used. Otherwise, in our houses, the motor is induction motor only. Okay. Yeah. Okay. Some doubt, some of the students says at starting rotor poles cannot catch the speed of stator poles, that synchronous speed of RMF. So that synchronous motor is not, yes, synchronous motor is not self-starting like that only. Okay, right. Sir, how many days synchronous motor will take approximately? We are almost coming to the close. Synchronous motor, other than this, next class, almost we are going to close. Next, minimum 2, maximum 3 hours, 3 classes, we are going to close our topic. Tomorrow, class is not there. Okay. This may be Monday is not there. Tuesday, Wednesday. Mostly it is from here onwards. You leave this class. Today class is over now. Yes. Next, 2 or maximum 3 classes. That we are going to complete our entire syllabus. Okay. Now coming to our topic. See, are you ready? Yes. Yeah. Let us see why synchronous motor is not self-starting and how the motor can be started. Okay. See, synchronous motor, when supply is given to the stator, I will take 2 instances. Okay. Yeah. This is North Pole. This is South Pole and North Pole. North Pole. Here this is North Pole and South Pole. After some time, okay. I would like to take for 180 degrees rotation. For example, frequency of supply. Supply frequency 50 hertz say, then what is its time period? Time period is 1 by 50. 1 by 50 is equal to 20 milliseconds. 20 milliseconds. 20 milliseconds. So this is time period, na? This is time period is equal to how much? 20 milliseconds. 20 milliseconds. But if you take one positive to positive, this to here, this is how much time? 10 milliseconds. 10 milliseconds means 180 degrees. 180 degrees. It's 180 degrees, right? Yeah. Listen. Okay. Here, students, see. This is South Pole. South Pole, the poles are rotating at synchronous speed. Poles are rotating at synchronous speed means after every 180 degrees, half rotation, poles will interchange, na? Yes. Poles are interchanging. This is South Pole, this is North Pole. If 50 Hz frequency is applied, time period 20 milliseconds, for every 20 milliseconds, it will rotate 180 degrees, 360 degrees. But for every 10 milliseconds, after 10 milliseconds, if you see, South Pole will come to here. South Pole will come to here, North Pole will come to here. Correct? Because for 10 milliseconds, say, South Pole is here, it is come to North Pole position here, North Pole will come to here. They interchange their position for every 10 milliseconds. For every half rotation, they will interchange their position. Soon after, when supply is given, the armature poles directly rotate at synchronous speed. Will they have any inertia? Tell me, stator poles, will they have any inertia? No, there is no inertia of stator poles. Stator is not rotating. Stator is stationary, but stator pole formation is there, na? Yes, when cross dot changes, poles will rotate directly. When supply is given, directly they will rotate at synchronous speed only. Or else stator poles also, RMF also started from 0 speed also, sir. 0 speed to 10 RPM, 20 RPM. Is it like that? No. Stator poles, there is no inertia. Directly current changes, na, current directions are changes. Based on that, stator poles rotate at synchronous speed directly. They will interchange their position for every half rotation. But will the rotor rotate directly at synchronous speed? For example, these are rotating at 3000 RPM, say. These are rotating 3000 RPM directly. Will the rotor rotate directly at 3000 RPM? No. Rotor has to start from 0 speed onwards only. Because due to mechanical inertia of rotor, no physical system, not only this. Due to mechanical inertia, rotor cannot rotate at synchronous speed directly. It has to start from 0 speed onwards. 0 speed, 10 RPM, 20 RPM, 100 RPM, right? 300 RPM, 1000 RPM, and it will take some time to reach its final speed due to its moment of inertia, due to mechanical inertia. No rotor can rotate. Every motor also used, even DC, induction, or any motor will start from 0 speed onwards only. So they will take some time to reach its steady state speed. But stator poles, they do not wait until whether rotor is rotating or not. They rotate directly at synchronous speed. Directly at synchronous speed. See, this is when these poles are rotating, rotor also will trying to rotate. Electromagnetic torque is in clockwise direction. Electromagnetic torque clockwise direction. South pole attract this north pole. No? The south pole of the stator attracting the north pole of the rotor. Clockwise direction. But rotor is at zero speed. When rotor is at zero speed, it will just rotate it some 1 degree, say. But by that time, stator poles are going far away. Stator poles are going far away. South pole is going, no further attraction. The north pole is coming to here. North pole is coming to here. But rotor is almost there only. Rotor north pole there only. Because they are rotating at 3000 RPM. This is at zero speed. Immediately, just within a very less time, the stator poles are going far away. North pole is almost there only. Then one north pole, what it will do? It will repel in this direction. So your electromagnetic torque will be in counterclockwise direction. Torque is counterclockwise direction. Again north pole is going, south pole is coming. Again it is attract. Like that, the rotor is subjected with clockwise torque and counterclockwise torque. Clockwise, counterclockwise. But it cannot develop the unidirectional torque. It cannot develop unidirectional torque. It is only subject with clockwise and counterclockwise torque. Average torque is zero during starting. In other words, for the production of unidirectional torque, what is the requirement? Already you are completed induction motors, and also we have seen production of the torque topic. The general statement is, for the production of unidirectional torque, listen carefully. For the production of unidirectional torque, two fields must be stationary. When south pole of the stator are rotating, north pole also should rotate with the same speed. Of course, there is some angle may be there, but relative speed must be zero. And south pole rotating, north pole rotating, then only continuously attraction takes place. Then only torque is unidirectional. The relative speed must be zero. Two fields must be stationary with respect to each other, right? But at the time of starting, the relative, what is the relative speed between stator poles and rotor? Rotor poles. Rotor is at zero speed. Rotor poles are at zero. Rotor poles are, right? Stator poles. Stator poles rotate at ns. But what is the rotor poles? Rotor poles is at zero speed, 0 RPM. And these are ns RPM. Rotor is at starting. Starting at a rotor, physically it has to rotate, na? Yes. Relative speed is ns. When relative speed is ns means average torque is 0. But for the production of unidirectional torque, what is the requirement? Two fields must be stationary with respect to each other. And can you tell me when you can expect a relative motion is 0? When rotor rotated synchronous speed. If rotor poles rotated synchronous speed, then only unidirectional torque will be developed. Unidirectional torque will be developed. That's the reason in synchronous motor, unidirectional torque is developed only at synchronous speed. Only at synchronous speed. That's the reason synchronous motor will always rotate only at synchronous speed. Only at synchronous speed. At any other speed, less than or more than synchronous speed, synchronous motor will develop, the torque will be, average torque will be 0. Okay. Can you tell me induction motor? What happened in induction motor? Already you are completed. Induction motor, rotor rotate less than synchronous speed. Rotor rotated less than synchronous speed. But in the rotor also RMF is produced. When rotor rotate less than synchronous speed, rotor conductor cut the flux. Then EMF is induced in the rotor conductors. Then rotor poles also formed, but the poles are not separately excited. Synchronous motor, we are exciting poles are separately, but induction motors, poles are, right, induced poles. And when rotor rotate, stator synchronous speed 1500 RPM, say, for 4-pole machine. Stator poles rotate 1500 RPM. Rotor rotate 1400. But on the rotor, again, poles rotate slip speed. Rotor 1500, but rotor poles speed is extra 100 RPM. Totally what happened? Rotor rotated 1400, on the rotor again 100 RPM. And totally, so two fields are stationary. At what speed the rotor may rotate? Induction motor, unidirectional torque is developed at every speed. Whatever may be the speed, even at zero speed also. Induction motor, zero speed. Can you tell me one point I will ask? Induction motor at zero speed. Right? When rotor is zero speed, on the rotor poles at what speed they will rotate? NS only. Because when rotor is at zero speed, slip is 1. You are giving 50 Hz frequency to the stator, rotor frequency also 50 Hz. And the rotor poles also rotated synchronous speed. Now, even at zero speed also, two fields are stationary. Unidirectional torque is developed. And as rotor starts rotate, what will happen? Rotor frequency decreases. If rotor is rotating 1400 RPM, say, rotor rotate 1000 RPM, say, 1000 RPM, the frequency is induced frequency is such that it will develop on the rotor RMF, so 500 RPM. The frequency is like that 500 RPM. If rotor rotate from 1400 RPM, say, the frequency is decreased and slip speed. The RMF is there now, it will rotate. The rotor speed is different, rotor RMF speed is different. In induction motor, rotor speed is different, rotor RMF speed is different. Rotor 1400 means on the rotor RMF 1400. Total how much? 1400 plus 100 is equal to 1500. This story you know. Can you tell me, dear students, can you tell me when our synchronous motor rotating at zero speed, when rotor is zero speed, what is the speed of the rotor poles? Rotor poles also zero. The rotor poles are not induced poles. They are separately excited. DC current is given. Don't expect any rotor is rotating zero speed, rotor poles rotate 100 RPM, not like that. Where rotor is there, poles also there. If rotor is zero speed, poles also zero speed. Rotor is itself poles. When rotor rotate, then only poles will rotate. Rotor rotate, then only poles will rotate. Right? Rotor is itself poles. When rotor rotated 1000 RPM, then rotor poles rotate 1000 RPM. If rotor rotated 1500, rotor poles also 1500. Therefore, when rotor rotated synchronous speed, then only two fields are stationary. If rotor rotated synchronous speed, then only rotor poles rotated synchronous speed. Then only both are stationary. That's the reason synchronous motor will rotate only at synchronous speed. Unidirectional torque is developed only at synchronous speed, no other speed. No other speed. Other than synchronous speed, its torque is zero. Average torque is zero. So it will develop only unidirectional torque only at synchronous speed. Because common sense is when rotor rotated synchronous speed, then only rotor poles rotated synchronous speed, then only stator poles and rotor poles are stationary, then only unidirectional torque will be developed. That's all. But when rotor is zero speed, starting condition, relative motion exists. But we want relative motion is zero, na? Yes. So during starting, relative motion exists. Two fields are not stationary. That's the reason no unidirectional torque. Hence, the synchronous motor is not self-starting. And then how to start the synchronous motor? The synchronous motor can be started. Inertia, all this problem is due to inertia. Then what to do? You have to rotate the rotor by some means, by using extra motor that we are going to see, DC motor or induction motor, a pony motor, right? Or damper winding starting. Somehow you have to develop you have to rotate the rotor. You have to bring the rotor near to synchronous speed such that inertia reduced to zero. You have to rotate. But once it is started, say, then unidirectional torque will be developed by synchronous motor action. Okay. Yes. So the problem is that starting, relative speed is not zero. Let me write all these things. Okay. See, during starting, when supply is given to the stator, when the supply is given to the stator, stator poles rotated synchronous speed. Stator poles rotated synchronous speed. Stator poles rotated synchronous speed. Okay, yes, they interchange their position. They interchange their position. Their position at every half rotation. At every half rotation. Half rotation. No mechanical inertia. No mechanical inertia for stator poles. Stator poles. Soon after supply is given. Soon after supply is given. They directly rotated synchronous speed. They directly rotated synchronous speed. Rotated synchronous speed. Synchronous speed. But the rotor poles, could not able to catch up the speed of stator poles. The rotor poles cannot able to catch up the speed of stator poles due to mechanical inertia. But the rotor poles could not able to catch up. Could not able to catch up the speed of stator poles. Stator poles due to mechanical inertia of rotor. Due to mechanical inertia of rotor. Due to mechanical inertia of rotor. And rotor is subjected with clockwise and counterclockwise torque. The rotor is subjected with clockwise and counterclockwise torque. Clockwise and counterclockwise torque. So that the average torque is 0. So that average torque is 0 during starting. During starting. In other words, during starting. Hence, the synchronous motor is not self-starting. Hence, synchronous motor is not self-starting. Is not self-starting. And in other words, there exists relative motion between. There exists relative motion between stator poles and rotor poles. Relative motion between stator poles and rotor poles. Stator poles and rotor poles, which is equal to synchronous speed. Which is equal to synchronous speed. Synchronous speed at starting. Synchronous speed at starting. But for the production of unidirectional torque, what is required? Two fields must be stationary. But for the production of unidirectional torque, okay. But for the production of unidirectional torque, the two fields, that is stator field and rotor field. Stator field and rotor field. Or stator poles and rotor poles. Stator poles and rotor poles. The two fields must be stationary with respect to each other. Must be stationary with respect to each other. must be stationary with respect to each other for the production of unidirectional torque. Right? Yes. But whereas during starting, relative speed is ns. In other words, when rotor rotate at synchronous speed, then only rotor poles rotate at synchronous speed. When rotor rotated synchronous speed, when rotor rotate at synchronous speed, then only rotor poles, rotor poles rotate at synchronous speed. Rotor poles rotate at synchronous speed. Rotor poles rotate at synchronous speed. Then only unidirectional torque is developed. Unidirectional torque is developed. Correct? Yes. Unidirectional torque is developed. In other words, that's the reason synchronous motor rotate only at synchronous speed. That's the reason synchronous motor rotate only at synchronous speed. Other than synchronous speed, the average torque will be 0. Only at synchronous speed, unidirectional torque is produced. There is no RMF on the rotor. Just like induction motor. Since the poles are separately excited, yes, the poles are separately excited. When rotor rotates, then only poles will rotate. Since rotor is excited with DC, okay. When rotor rotates, then only rotor is itself poles. See, the poles are formed. The rotor is itself behaves as a poles. The rotor is itself act as poles. Rotor itself act as poles. So when rotor rotate, then only the poles will rotate at synchronous speed. Okay. But whereas in induction motor, when rotor rotated less than synchronous speed, there will be rotor RMF. Okay. So therefore, when rotor rotate, then only rotor poles rotate. Whereas in induction motor, on rotor also rotor RMF is produced. In induction motor, RMF is produced on the rotor, which will rotate. RMF means what? Rotor poles. In other words, rotor RMF means rotor poles. And the rotor which will rotate at slip speed with respect to rotor. Okay. But here, not with respect to rotor. Rotor a pole a rotor. Because their poles are induced poles. Induction motor poles are induced poles. Poles are produced or induced. That is, the poles are induced poles. Induced poles in induction motor. Induced poles. The induced poles will rotate at synchronous speed. Okay. So I don't want to go in detail about that induction motor. Already you are completed, right? Only thing is here, rotor, there is no rotor RMF. No rotor RMF. It is not AC. Correct? When rotor rotates, then only poles will rotate. And then how to start the synchronous motor? Synchronous motor can be started by applying an external means. Synchronous motor can be started by applying an external force. By applying an external force to reduce the inertia. External force to reduce the inertia. When excitation is given, it will rotate at synchronous speed to reduce the inertia. Can be started by applying an external force to reduce the inertia. Okay. Then there are various starting methods are there. Starting methods. Let us see. One method we will see, then we will close. Starting methods of synchronous motors. How the synchronous motor can be started? Starting methods. Starting methods of synchronous motor. Starting methods. The various starting methods. Number one, first one is auxiliary motor starting. Auxiliary motor starting. Auxiliary motor starting. That is by using DC motor. By using DC motor or induction motor or a pony motor. Pony motor. Induction motor, pony motor. Pony motor. Second one, induction starting or damper winding starting. Damper winding starting or induction starting. Damper winding or induction starting. Damper winding starting or induction starting. Third one is synchronous induction motor starting. Synchronous induction motor starting. Synchronous induction motor starting. But the first and second methods are used starting under no load condition. 1 and 2 can be used are starting under no load condition. The first methods for starting under no load condition. Under no load condition. No load or light load conditions. But third one is there now, that is starting under load condition. Starting under load condition. Okay. Starting under load condition. Yeah. So let us see the first method, then we will start. Auxiliary motor starting. So let us see first one, auxiliary motor starting. Auxiliary motor starting. Okay. Auxiliary motor starting. Auxiliary motor starting. In this, stator is connected later. Okay. Is a field, and auxiliary motor is coupled. Auxiliary motor is mechanically coupled to this. See, this is the auxiliary motor. Is mechanically coupled. Mechanically coupled. This is auxiliary motor. The auxiliary motor may be this may be a DC motor, or it may be an induction motor, or it may be a pony motor also. Right? But at the beginning, supply is not given to the stator. Stator, it is open circuited. Stator is open circuited. Okay. Listen. Why it is open circuited? Because if supply is given at the beginning, what is going to happen? Rotor is, it cannot rotate. Rotor is 0 speed. When what is the back EMF in that? Back EMF is 0. Back EMF is 0. At n is equal to 0. At n is equal to 0, what is E? E is equal to 0. Then what is the current IA? IA is equal to V minus E by ZS. Is very, very high. That is equal to simply V by ZS is very high. Is very high. Is large. Therefore, to limit that current, and I cannot give V. When I will give V? After E is coming. When E will come, when rotor rotate, then only E will come. After starting that, then I will give. Okay. So V is not given at the time of starting. Therefore, at the time of starting, the stator winding, stator is not excited. Stator is not excited. Is not excited. Stator is not excited. Therefore, current is 0. Therefore, current is 0. Therefore, IA is 0. Armature current is 0. Armature current is 0. And stator will be given. Stator will be given with the after rotation. Once rotated, say, then E will come. Back EMF. Where back EMF will be? In the armature winding, back EMF will be there, na? Yes. In the armature winding, back EMF will comes into picture. That back EMF is also required. But at the 0 speed, back EMF is 0. Right? Yeah. So that's the reason it cannot be given. It will be given later. See. When field current is given, see, based on the field current, if it is acting as a north pole, it is acting as a south pole. This is the supply voltage is V. Supply voltage is V volts. Its frequency F, say. Stator is not given, but rotor is driven with the rotor will be driven with, the rotor is rotated by the auxiliary motor. Rotor is rotated auxiliary motor. As speed increases, its inertia decreases. Na? Inertia decreases. But when rotor is rotating at the same time, what will happen? Back EMF will comes into picture. Fine. It is cutting the flux. EMF is induced in the armature winding. And rotor is driven near to synchronous speed. Near to synchronous speed. So for example, it is almost some synchronous speed 3000 RPM say. We can rotate nearly up to, right? Nearly up to some 2900 RPM. By that time, inertia reduced to 0. And when already rotor is rotating, rotor is rotating. At what speed? Nearly, it is nearly rotating at some 2900 RPM say. 2900 RPM it is rotating. Inertia reduced to 0. Inertia reduced to 0. It is driven by auxiliary motor. Now what we will do? Give the supply to this. Then close the switch. Stator is excited. When stator is excited, stator poles will form. South pole and north poles are formed. They directly rotated 3000 RPM. They directly rotated 3000 RPM. Then the south pole, what it will do? It will pull the rotor because rotor is already inertia 0. Now it can pull quickly. At 0 speed, it is problem, but almost it is rotating. Na? Then due to the magnetic locking, what the south pole will do? It will pull the rotor. Similarly, the north pole of the rotor will pull. So this is pulling, and finally it will rotate at 3000 RPM. Rotor will rotate at 3000 RPM. Due to magnetic locking, the rotor will rotate at synchronous speed. This is the starting method. It's very easy. Nothing is there. By using extra motor, we are rotating near to synchronous speed to reduce the inertia to 0. 0, fine? Yes. Nearly synchronous speed. And when supply is given, say, when supply is given, stator poles are formed, and the stator poles will pull the rotor. Due to pull-in torque, some extra torque is developed. The torque is called pull-in torque. So pull-in torque is related to starting condition. Due to pull-in torque, rotor poles are pulled into synchronism with the stator poles, and from there onwards, the rotor rotated synchronous speed. From there onwards, rotor rotate only at synchronous speed. This is starting. Okay. Now tell me, once this motor is started, what do you do this auxiliary motor? What we will do auxiliary motor? It is started. Then no use of this motor. Then what we will do is, we cannot decouple mechanically. No, mechanically it is rotating at 3000 or 300 RPM. Say you cannot decouple mechanically. You want to decouple means again you have to stop that setup. Then you have to open nut side bolts. But once you have stopped means our synchronous motor also will stop now. So mechanically not possible. It is already started motor. Then what we will do is simply disconnect its supply. That's all. The supply will be disconnected. The motor is disconnected from its supply. Motor is disconnected, and the motor will be still rotating by synchronous motor. On the shaft, it is just rotating. Just rotating because it is a small motor. It is small. For example, synchronous motor is 100 kilowatt motor, say. Synchronous motor is, if it is 100 kilowatt motor, and this will be 1 kilowatt motor is enough. 1 kilowatt motor is enough. 1% is enough. Because that's the reason we are starting under no load condition. Dear students, I have given this method is used starting under no load condition. Why? Because no load condition, small power is enough. Just to only to meet the frictional losses, na? Yes. If you are starting at full load condition, say, on the synchronous motor again 100 kilowatts load is kept, mechanical load has kept up, then the load torque has to be developed by this auxiliary motor. If it is 100 kilowatt means then what will be the rating of the auxiliary motor? 100 plus 101 kilowatt motor is required. If you start under load condition, it is 100 plus 101 kilowatt. So that's the reason it is started under no load condition. No load condition, though motor is 100 kilowatt, load is not there. So 1 kilowatt motor is enough. And once started, disconnect the supply. Disconnect the supply for the auxiliary motor. Okay. And it will be readily available. For example, sometimes what happens, supply failure takes place. Sometimes again the supply failure takes place, say. For example, the supply failure takes place. Supply fails. Then what happened? When supply fails means again motor stop. Motor stop. When motor stop, again you have to start now. How to start? Again our motor is available. This motor is available, auxiliary motor is available, again we will start. That's the reason it is permanently connected. Permanently connected. But once started, then simply, once started means simply we will disconnect this. We will disconnect this motor. With a small motor, let them rotate later also. If it is DC motor, say, if it is a DC motor and the same DC motor can be used as an exciter to excite the field of synchronous machine. This field is there now. What we will do? Output of this DC motor. Once it is started means DC motor will act as a DC generator, shunt motor. Can be used as a shunt generator. The output of DC shunt generator will be given to excite the field of synchronous motor. The same can be used to excite the field. I can remove this battery, external supply. The output of the DC shunt motor itself will be given. If it is induction motor, we cannot utilize. Simply it will rotate. Pony motor also same. But pony motor also induction motors. But 2 poles less than the number of poles of synchronous motor. I will come to the reason. But synchronous motor 20 poles say, induction pony motor 18 poles, 2 poles less. For smooth starting, I will explain why it is. First, let me write these things. Now, auxiliary motor is mechanically coupled. Yes. Auxiliary motor is mechanically coupled. Mechanically coupled and driven, mechanically coupled to the shaft of synchronous motor. Shaft of synchronous motor and driven near to synchronous speed. And driven near to synchronous speed. Synchronous speed so that inertia reduced to 0. The inertia when it exists only during starting. At 0 speed inertia is more. 0 speed inertia is more. But once started inertia will reduce. So that inertia will reduce. When supply is given to the stator, the stator poles are formed. Stator poles are formed. Stator poles are formed and they rotate at synchronous speed. And rotated synchronous speed. Then the rotor pulled into synchronism. So now when south pole is coming now, under north pole, it will pull. Then the rotor will pull into synchronism with the stator poles due to pulling torque. Then the rotor poles. The rotor poles pulled into synchronism. With the stator poles. Due to pull in torque. From there onwards, rotor rotated synchronous speed. From there onwards, rotor rotated synchronous speed. Okay, yeah. This is a starting method. And once motor is started, the auxiliary motor is disconnected from the supply. Auxiliary motor is disconnected from the supply. Auxiliary motor is disconnected from the supply. If it is a DC motor, the same can be used as an exciter. The same can be used as an exciter. As an exciter to excite the field of synchronous motor. We excite the field of synchronous motor. Okay, the same can be used as to excite the field of synchronous motor. And pony motor. Pony motor is a small induction motor. Pony motor also a small induction motor only. A small induction motor with two poles less than the, pair of poles, 2 poles less than the number of poles of synchronous motor. Number of poles of synchronous motor. 2 poles less than the number of poles of synchronous motor. Two poles less than the number of poles of synchronous motor. Okay. Let us see why. Why reason? Why reason like that? Okay. Reason is for smooth starting. Okay. Poles of pony motor. Poles of pony motor is equal to poles of synchronous motor minus 2. Poles of pony motor is equal to poles of synchronous motor minus 2. For example, if poles of synchronous motor is equal to 20, say 20. Poles of synchronous motor is 20. Then poles of pony motor. Poles of pony motor is equal to 20 minus 2, 18 poles. 18 poles. Reason is for smooth starting. Reason is for smooth starting. Reason is for smooth starting. Just let me explain why it is, how it is smooth starting, and what is the reason behind the coming to 2 poles. Okay. Yeah. See, reason is reason why 2 poles less than poles of synchronous motor. Why the poles of pony motor? Why the poles of pony motor is less than the number of poles of synchronous motor. Okay, as I told now, poles of pony motor is equal to poles of synchronous motor minus 2. Let us discuss. That is, for example, this is our synchronous motor. Yeah. This is a pony motor. Auxiliary motor. Auxiliary motor is a pony motor. Okay. See. Pony motor, if synchronous motor poles, let us take poles of synchronous motor is equal to 20, then poles of pony motor is equal to how much? 20 minus 2, that is 18. Let us discuss this. When poles of 20 means what is the synchronous speed? When poles, if poles of synchronous motor is 20, say, then the NS is equal to 120 into F by P. That will be 300 RPM. 300 RPM for 50 Hz frequency. For 50 Hz frequency, poles are 20 poles and frequency 50 Hz. Say frequency 50 Hz. What is the NS? NS is equal to 300 RPM. The stator poles will rotate at 300 RPM, na? Yes. Stator poles rotated 300 RPM. That is expected. Fine, yes. And instead of that, if poles of pony motor also equal to 20, say, then its speed also same. Then its synchronous speed is 300 RPM. 300 RPM. But what is its actual rotor speed? NR will be less than NS because it is induction motor. If you take poles of pony motor is equal to 20 means it will settle at what speed? Less than synchronous speed. Less than synchronous speed only. The NR is equal to some 250 RPM, say. 250 RPM. Say, less than synchronous speed, correct? Yes. But finally, rotor will settle at what speed? 250 RPM. It is settled at 250 RPM. 250 RPM. And when supply is given, see, 250 RPM, okay. When supply is given, stator poles straight away rotated. Stator poles straight away rotated 3000 RPM. 300 RPM. Then rotor will pulled into synchronism from 250 to 300 RPM. Sudden jumping, 250 to 300 RPM, suddenly it is jumping. Suddenly jumping. Correct? Yes. And to avoid that, what we are doing to avoid that, if poles of pony motor is equal to 18, say, 18 for 50 Hz frequency, its NS is equal to 333 RPM. 333 RPM. Then its rotor speed NR is equal to nearly 300 RPM. That is what we require. Nearly 300 RPM. Almost 300 RPM, say. Well and good. 1 RPM this side does not matter. 300 RPM. That is nearly equal to NS. Correct? Equal to, it should be nearly equal to this is synchronous speed. Nearly equal to. That is what we want for smooth starting. And when supply is not there here, when supply is not there, if it is given with that not 250 RPM, it is almost 300 RPM rotating. 300 RPM means when you give the supply, what is going to be happen? When supply is given, say, directly this pole 300, this pole 300, without any jerk. Without any jerk, rotor will rotate at synchronous speed. Okay. That's what it is required. That's the reason two poles are selected. Actual rotor speed is nearly equal to synchronous speed. By selecting, the reason is by selecting two poles less than the rotor speed of pony motor is nearly equal to synchronous speed. Synchronous speed of synchronous motor. So that smooth starting. Okay. This is the reason. Fine. So with this, we are completed our topic. So our starting method is completed. Next method, induction starting, it won't take much time. And thereby phasor diagram, power flow equations, vehicles, inverted vehicles. With that, we are going to close our synchronous motor. Okay. Yeah, exactly around 8:87 we are closing. Fine. Any doubts are there? You can ask and then. Yeah. Yeah. Yes. Anyone is there?
Hello.
Hello.
Yes, sir.
Tell me.
Good evening, sir.
Good evening.
Sir, why we are not using this method under loading condition?
Loading condition also pony motor. What should be the rating of pony motor? If you are using 100 kilowatt motor loaded, then entire load has to be supplied by pony motor only, 100 kilowatt motor. But once started, what is the use of that motor? Not only pony motor, any motor, auxiliary motor.
Yes, sir.
If you are using 100 kilowatt synchronous motor to start, but the motor is loaded, say, who has to supply that load torque? Pony motor only or auxiliary motor has to supply. And that rating also must be equal to 100 plus some extra. The auxiliary motor has to rotate that synchronous motor as well as load also. How long time it will be? Only for small duration. But once started, no use of this motor. So that is more cost unnecessary, no?
Yes.
That season started under no load condition, and once started, motor can be loaded.
Okay, sir.
Motor can be loaded. Okay.
Sir, once open page 14, F14, sir.
Huh?
Page 14, sir.
Okay.
Yes, sir. I want to take screenshot, sir. Wait, sir.
Okay. Okay. Hello. Okay. Hello, anyone is there?
Hello, sir.
Hello. Tell me.
Hello, sir. In constant excitation from varying prime or variation, that problem. Sir, how you justify the equation E is equal to V plus J times the IAXS?
Where?
In constant excitation, but prime or input is variable.
Everywhere it is valid. Everywhere E and IA exists, it is valid.
Sir, in that case, EMF and terminal voltage are same constant, right, sir?
EMF constant, terminal voltage, magnitude is constant.
Yeah, magnitude constant, but current is varying.
How current varies? That's what I told. Phase are
different. but according to that equation, sir, it equated to 0, right, sir?
Not zero. Phase difference will E at an angle delta. Don't take it is difference. E is equal to, what is that? E at an angle delta, V0. Okay. There is a phase difference is there, na? Phase difference.
Yes, sir.
V 230 volts, E also 230 volts.
Yes, sir.
I is equal to E delta minus V0 by ZS. Is the current is 0, na? No.
No, sir.
Phase difference. Delta is responsible for current flow. That was I will repeat it. Though magnitudes may be same or magnitudes may be different. And I don't think E may be more, E may be less also. It is not a matter. Though E constant, delta as mechanical power input increases, rotor poles leads more angle. You are pushing with the rotor prime mover. Rotor poles leads, EMF leads. Phase are difference. AC means phase are difference is responsible. Magnitude not necessarily. I think you will be knowing. Alternator I have drawn E less than V also. Some magnitude E4 I have given excitation E less than V. Even though, in alternator, rather DC generator EG always greater than V.
Okay.
Synchronous generator EG may be more or less or also equal. Then reactive power, reactive current, IA sin phi component may be either direction. That's the reason. But IA sin phi is always IA cos phi, always upwards. It will give always to the grid.
Yes.
Okay.
Thank you.
Phase are difference.
Okay.
Okay.
Hello, sir.
Hello.
Good evening, sir.
Good evening.
Sir, when you said a case that 2900 RPM, when we are rotating it nearly 3000 RPM.
Nearly 3000. Yes.
3000. Then when we are closing the switch, first we are not closing the switch because high current flow.
No. First you close the switch. EMF is 0, right? 0 speed.
EMF is 0. So V minus E will be tends to 0 because for no speed. If it no, no then
current
high
will
current.
be very high. Easy. Current is very high. At that
Sir,
time, one thing you can do, if you want, you can use a starter also, star delta starter. That you can use, okay, no issue. And then there is not necessary also to give. Why to give starter also not required? Why? Because I'm open circuiting, because I'm expecting large current. Simply open circuit.
Okay, sir.
Open circuit and you connect the after starting.
Okay.
Now,
After
tell
that,
me what is your
then
point?
after that, once it will rotate, means the rotor will be continue to rotate because of that. After that jerk, it will be continue to rotate.
Yes.
Then we have to remove that supply.
Which supply?
That is the auxiliary motor.
Auxiliary motor supply can be disconnected.
Okay, sir, please, on the last, do you make a problem on that how power flow is from motor to generator? If that speed will be DC motor is more, then it will be provide power to the synchronous motor.
Sorry, repeat.
Sir, there is some mixed problems are in gate, sir. The power is flow from motor to the generator side, or that is synchronous side, means from DC side to SC side.
DC, where is the DC?
So, sir, there is some problem. Actually, I am talking about at the end of class. Some questions on mix means only not synchronous machine. That is synchronous machine with DC. Do some
I'm not getting where power flow from DC to AC, how it is taken. Where is that question?
I think that 1 kilowatt, na? That auxiliary motor is 1 kilowatt.
Okay.
And it is 100 kilowatt. Then if auxiliary motor is provide 1 kilowatt, na? Starting in the starting.
Yes. And 100 kilowatt synchronous motor, okay. But is it loaded? When it will take 100 kilowatt? If it is mechanically loaded. Say synchronous motor, no load, 100 kilowatt motor is there. Okay, fine. I am not connecting any load. You connect the supply. Will it take 100 kilowatt?
No.
It won't take. When load increases, it can be operated 50 kilowatt also. Maximum rating is 100 kilowatt.
Like a parallel operation of that generator, how we are dealing with.
Yes. How much load you are connecting, that much power it will take. That's the reason I am not connecting load at the beginning. First, I am simply starting. And after starting, then we can add the load.
Thank you.
Yeah. Your questions we will see later. No problem. after that class completion also, my phone number is there now. You can ask after completion of our topic. Okay, right.
Hello, good evening, sir.
Hello, yeah, tell me.
Sir, one just doubt is there. Sir, we
Ah.
have two methods, no, sir. One from the excitation, another is the prime mover input.
Yes, yes.
Sir, if we are talking about one by one, if we take at a time, excitation and the prime mover changes, what will happen, sir?
Yes, yes, yes. Now you mean say, why to discuss two cases? Why can't two cases cannot be clubbed? Then you will increase excitation as well as you will increase the prime mover input. Huh?
Yes, sir.
If you use like that, theoretical discussion cannot valid, not valid, cannot be continued. A problem is being given, say, then we can say answer what is going to be happen. Which effect is more, that will leads. For example, excitation is how much increase? 20%. Prime mover input is increased by 30%, say. With that, I will calculate with the numerical values, and end results I will say only with results. What is this is going to be happen. But we cannot say just like that. Due to this much increase and the power factor lagging or leading means you cannot say.
Okay, sir. Means based on the theoretical problems.
Theoretically, you cannot say. Theoretically, conclusions we cannot say. One effect we can derive conclusions.
Okay, sir. Is it any expectation from that both means at a time you can ask that questions?
Problem can be asked. Problem means in the morning I have we did one problem. Excitation is increased 25%.
Yes, sir.
1.25. The prime mover input, their power I have taken constant, no?
Yes, sir.
Power P dash is equal to P. But if it is power also increase some 10%, say, now P dash is equal to 1.5 I will take. So that both equation you have to solve. Examination you won't give like that. You won't give. If it is given like that, say it is time consuming. It becomes conventional problem.
Okay, sir.
It becomes
Sir,
problem. Lengthy.
Okay. Sir, one more. In synchronous method, we are using three methods to starting the synchronous motor, no, sir. Sir, in presently you are using means we are using three methods, or we are using any new technology in that?
Yeah. Synchronous motor means actually from stator side also, that is what I am going to explain at the end. From stator side, by using cycloconverter, I will reduce the stator field speed only. I will connect stator poles instead of rotating very fastly. Frequency you give some 10 hertz, say. Its speed is less. Na?
Yes, sir.
One hertz you give, slowly they will rotate. Then rotor also will rotate slowly. As rotor speed increases, now I will increase the proportionally stator field speed. Gradually I will increase so that inertia reduces. Gradually I will increasing. Slowly I will bring up that rotor to synchronous speed. That also can be done. Normally generating stations are there, na? Pumped storage plants.
Yes, sir.
And mainly, even we cannot use auxiliary motor. Generally, induction starting is there, damper winding starting generally used.
Okay.
Pumped storage plants, same machine can be used as a generator and also motor, na?
Yes,
For
sir.
starting purpose, their damper winding starting. Damper winding. Induction, it will start like an induction motor.
Okay.
When excitation is given, after starting excitation, they will give, then it will act as a synchronous motor. That is the next method is there, na? That is what.
Okay. Sir, we are using in pony motor for the smooth starting less than the 2 poles, no, sir. Sir, is there any chances for in DC motor, because there can be used as a DC motor as an exciter, no, sir? Is there any chances to for the smooth rotating as in induction motor?
What is your doubt? I am exactly not getting.
Sir,
DC motor you are using, okay.
Sir, DC motor we have one advantage as the exciter.
Yeah, same can be used as an exciter, correct.
Okay, but we have using an induction motor for the smooth starting, means we are using the 2 poles. It act as a pony motor.
That is only called pony motor. If just to use induction motor with same equal number of poles, so that is called induction motor.
Yes.
And then there is a speed difference will there. Speed difference exists. It's not smooth starting. If pony motor means induction motor only 2 poles less than, then its rotor speed, actual rotor speed is closer to synchronous speed. That is what.
Okay, sir, just one small means is a like told.
Ah.
Sir, is there any chance in as a DC motor for the making a smooth starting as in pony motor?
Yeah, you can also do. By using DC motor, I can adjust its speed closer to synchronous motor, synchronous speed. DC motor speed can be easily controlled, na?
Yes, sir.
By field method or whatever, I will bring the rotor to whatever speed you want, you can bring it.
Okay. Because we have one excitation means one advantage as the exciter.
Yes. That can be done. That also can be done.
Okay.
But
That's all, sir.
mainly induction damper winding is there, na?
Yes, sir.
For damper winding, nothing is required. Directly, when you are connecting another motor, the problem is again it will rotate length, space occupation, all those things. But damper winding, anyhow, you are providing. Damper winding will do two functioning. Starting
Hunting.
will start as well as hunting also.
Oh, yes, sir.
Okay.
Okay, sir. Thank you so much, sir.
Okay. Right. Okay. So I'm closing the session.
Hello.
Hello.
Sir, can you please give your number?
Huh?
Can you please give your number?
My phone number I have given, 9849 719672. This is my. Okay. Yeah. Right.